I'll now call to order the Society's 2,394th meeting in the 148th year since its founding in 1871. Good evening, everyone. My name is Larry Milstein. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests to the Society's 87th Annual Joseph Henry Address, and tonight's lectures on Cassini's spectacular Saturn in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C., including our members and friends around the world who we hope are watching the live stream of tonight's meeting on PSW's YouTube channel. Joseph Henry was the first secretary of the Smithsonian Institution, the preeminent physicist of his time, and the founder of the Philosophical Society of Washington, PSW. We honor him tonight with this evening's series of lectures. Because we have a different format tonight, we will forego some of the usual preliminaries. The minutes of the last meeting will be posted to the website shortly, and if there are any corrections to those, please contact corresponding secretary at philsoc.org and let us know. Please join me in thanking the sponsors of the Fall 2017 and Spring 2018 lecture series, the Policy Studies Organization, in cooperation with the American Public University and a generous anonymous donor. Also, please join me in thanking the sponsor of tonight's Joseph Henry Address, the law firm of Mill and White, Solano and Brannigan. I'm pleased to announce that the following new members have been elected to the Society: Natasha Burns, an associate professor at the University of Texas, San Antonio; Joseph Fackler, a senior microbiologist at Adaptive Phage Therapeutics; Kevin Cassidy, an executive at Clear Focus Technologies; Angela Phillips Diaz, executive director, government research relations for UC San Diego; and tonight's speakers: Julie Webster, Phil Nicholson, Bonnie Buratti, Terry Hurford, and Conor Nixon. Please join me in welcoming them to membership. All new PSW members are invited to pick up from me a signed copy of Volume 1 of the PSW Bulletin, if you did not already receive one. And all members in good standing are invited to purchase a lapel ribbon, or rosette. Please see Social Media Director Ann McQueen to purchase a rosette, and if you already purchased one, to pick yours up. She will be at the back of the room after tonight's program. We now turn to tonight's lectures on Cassini's spectacular Saturn. Cassini was the largest spacecraft ever sent to the outer planets, over 12,000 pounds at launch. It was 2 decades in the planning and construction before it was launched in 1997. It took 7 years and several gravitational assists to finally reach Saturn in 2004. Along the way, it flew by Earth, Venus, an asteroid, and Jupiter. It explored Saturn's complex system of moons, moonlets, and rings for 13 years in a choreograph of almost 300 orbits, encompassing 162 targeted moon flybys, including 127 flybys of Titan and 23 of Enceladus. And it sent the Huygens probe to Titan's surface. Cassini traveled almost 5 billion miles and collected and sent back to Earth from over a light hour away more than 635 gigabytes of data, including more than 450,000 images. Cassini discovered 6 new moons of Saturn, an underground ocean and geysers on Enceladus, and methane lakes on Titan, to name just 3 discoveries. The data from its 12 instruments has provided the basis for more than 6,500 technical papers. Among the most successful deep space missions ever carried out, Cassini revolutionized our understanding of Saturn, planetary dynamics, and the possibilities for life in the solar system and elsewhere. The 5 lectures in this program will convey some of Cassini's rich history, its engineering, and what we know about Saturn, its rings and its moons, especially Enceladus and Titan. The lectures will also touch on the possibility for life to have evolved on Enceladus and Titan, and on future missions back to Saturn to look for it. Please hold questions for the question and answer period at the end of the lecture, when all 5 of our speakers will be together on the stage to field and answer your questions. And please join me in welcoming Vice President of PSW, Mark Clampin, to the podium to introduce our first speaker.
So it's my great pleasure this evening to introduce each of our speakers. Our first speaker, Julie Webster, is the manager of the Cassini Spacecraft Operations Office and concurrently serves as chief engineer of the Juno mission to Jupiter. She has been at JPL for 25 years. JPL is the Jet Propulsion Laboratory in California. Her interplanetary spacecraft experience has been primarily in mission operations on Magellan, Mars Observer, Cassini, and now the Juno mission at Jupiter. Please welcome Julie Webster.
Well, thank you very much. Thank you all for being here. I was doing really good until I saw John Cassini in the audience, or he saw me. Now he's going to tell me when I lie about any part of this. So if he corrects me, I'll graciously accept that. So one of the best things about the format tonight is there's 1 engineer and 4 scientists. So the first thing I did was get to rip out all the science pictures, which I never could explain, out of mine, and I only have to talk about what I truly know about, which is the spacecraft. I do include this picture, though, because I think this picture was from 2006. It's one of the most marvelous pictures. It's taken at conjunction, so the sun is behind it, and you can see all the extra rings that you never can see in the light. But I want to start out with, and John, you just keep quiet. I want to start out with the fact that this whole thing started in 1977. So for 41 years, starting with the Voyagers and Voyager's Grand Tour, the whole Saturn, the Jupiter-Saturn experience really has been going on that long. And they launched in August and September 1977. And Voyager 2 launched first. I would say this is before my time, but it's not really. I was not being in an aerospace at this time. And took the longer route, and then Voyager 1 took the quicker route to Jupiter first, and then Saturn, and then Voyager 1 went on out of the solar system, and Voyager 2 continued on to Uranus and Neptune. Let's see if I can get my light so you can see here. The Voyagers are still being tracked today. They've got a few more years. They've got a 20-watt amplifier that's broadcasting almost 17 and a half light hours away. So you send a command this morning and you come in tomorrow afternoon to see if it worked. Very, very impressive. There's never going to be anything like them. I think I love the word audacious for these guys. That was an audacious mission. So when Voyager went to Saturn, what it saw was, and these are between the two, and I don't know which picture, but this is picture of Saturn from the Voyager cameras, picture of the rings, picture of the orange ball of Titan, and that was all that they got. They had nothing in the resolution of the cameras that could go down through that. And then the icy moon, Enceladus. And as soon as they got there in the 80s, the scientists started saying, we have to go back, we have to go back. So this was a reconnaissance mission, and by 82, we started trying for the Cassini and Huygens mission. So it took about 10 years, and I think we went back and forth with the Europeans. I don't know all of the history, but between Europeans going to build and the United States going to build the probe, and the Europeans were going to build the probe, and it wound up that the United States built the Cassini spacecraft, and the Europeans built the Huygens probe, which hitchhiked with us to Saturn. So Cassini is truly an international mission, and several people in this room know that that almost saved us from being canceled. When this was originally in 1992, a Cassini-Ana craft, Comet Rendezvous and Asteroid Flyby mission, and the craft mission was summarily canceled, and there was quite a fight to keep Cassini. This is a good picture of Cassini. It's sometimes it's called Battlestar Galactica. Sometimes I call it the Swiss Army knife, but it was bigger, better, better. Everything that you can imagine. The Voyagers went out with a spacecraft about that size, with a 3-meter antenna. We went out back to Saturn with a 4-meter dish, the magnetometer boom. It's about the size of a small space school bus. So it's about 23 feet in length, and we mix feet and meters intermittently. It depends on who you talk to. There was 12 instruments, 4 cameras carrying all resolutions. There was a radar in case we needed to radar image Titan. There was radio science, so this antenna was actually quite a unique antenna, and then it's a 5-frequency antennas. It was able to do 2 S-band frequencies, an X-band frequency, which was our main communications, a KU band for radar, and a KA band. So it worked from 2 gigahertz to 32 gigahertz. The probe, again, we'll talk about the probe in a minute, but there were, when you carry one, you carry, and you got to last a long time, and you're only going to build one flagship mission every 10 years. You carry 2 of everything. So we carried 2 radios, 2 computers, 2 whole propulsion systems, 2 guidance systems, 2 attitude cameras, 2 stellar reference units, and we used some of the backup units along the way. Let's see, we used 3 radioisotope thermoelectric generators, so 3 RTGs. The combined energy of these things were 850 watts at launch. We were down to 602 watts at the end of 2017. So half a hairdryer ran this whole mission. I love that as a fact. But I have to tell you, this is how I saw Cassini. This is how, when I close my mind, that's how I see Cassini. As a 12-sided bay with over 10 miles of wiring in it. And I was lucky enough to be part of the assembly, test, and launch operations team that wrung out every single wire end on this spacecraft. Amazing beast. This looks a little more like it. This is in the buildup. And of course, Earth is the worst atmosphere or environment we can put our spacecraft through. It's like if they can survive, some of the dumb things we do to spacecraft, they can survive almost anything. This is kind of what the probe looks like underneath its cute covering, and it always had to have cooling. There's a story for another time on cooling. This is a interesting cosmic dust bin. It's a cosmic dust analyzer. that became very important at the end. And then this is our society picture, all dressed up with all the thermal blanketing. The thermal blanketing, this stuff goes from 2 layers to 20 layers thick, and it's a layer of like mylar, layer of wedding veil scrim, layer of mylar, layer of wedding veil scrim, and depending upon how much heat it has to hold in or how much heat it has to reject is the thickness of it. There's a little bit, there's some things that are black, but most of Cassini was gold shield. These are the 4 cameras which the scientists will talk about tonight, not so much from the camera point, but the wonderful pictures that they got and the science that they got out of this program. So finally, launch was October 15th, 1997. And one of the things that's important to tell you about Cassini is, as opposed to what you saw with the Voyagers, how they went directly to Jupiter and Saturn, we were so heavy and so big that even with the biggest launch vehicle at the time, which was a Titan 4B, we still had to go here and then go by Venus and then swing out here and get a gravity assist, and then we had to slow ourselves down to fall back in to Venus to get captured, to get another gravity assist from Venus, and then we finally got back to Earth swing by. So almost 2 years later, we were right about where we started from, but moving much faster. And then it took us only a little over a year to get to Jupiter. We did a little bit of a swing by at Jupiter, not very close. I think we're about 600,000 kilometers away, but Jupiter's a big planet. And finally, July 4th, 2004, we arrived at Saturn. On the way, and these are the only 2 science pictures I keep in this thing, because I wanted to emphasize, on the way in, this is a picture of Phoebe, which is a captured Kuiper object. Did I say that right? This was Voyager resolution. So this is Voyager taken in 1980 and 81. This was Cassini's picture on the way in. And I do that not for the science, but how good the cameras were 20 years later. And this was 1995 technology. Can you imagine what it would look like if you could capture it today? So one of the big things that we had to do was we had to, of course, slow ourselves down to get into Saturn orbit. And so we called it Saturn orbit insertion. One of the things about being at Saturn is you're 90 minutes one-way light time away. So you do a 90-minute burn. So by the time the burn ended on the spacecraft, we were getting the first inkling that it was starting 90 minutes later. Cassini carried... This is kind of an interesting fact. Cassini carried almost 3,000 meters per second, or it carried 3,000 kilograms of bipropellant and about 132 kilos of hydrazine. But that was mostly used to get us there, to shape the orbits, and get us out there. We actually used Titan as we used the gravity assist far more. All we did with the Cassini spacecraft after we got into orbit, which used about 25% of the total propellant, we used Titan as the gravity assist to shape all the orbits. But we had a very specific thing, and we came through here, and here's the burn start. So we went through the rings, and then turned into the burned attitude, burn across here, and the burn in was timed by an accelerometer. If the accelerometer had failed, we would backed up on time. And then we came over and we were occulted by the Earth, and then we were solar occulted. So we actually, all of this happened before we even knew on Earth that it was completed. So it had to be self-sufficient. It had to work completely on its own. And about 3 years of my life were spent doing nothing but testing out every fault that could have happened along the way to make sure it was self-sufficient. And you can imagine what people come up with for faults. So the original tour was for 4 years, 2004 to 2008. We were going to go, and these are shaped by color. I think this one has the the 2010 in here. This is the Iapetus orbit. This is the Titan orbit in here. And so we came in here, flew by Saturn, got captured by Saturn's gravity, and then swung ourselves way out, did a burn here to slow ourselves down, and then came back around to drop off the probe. So you're looking at gravity. So here's the Earth, here's the size of Enceladus, and here's the size of Titan. And yet Titan gave us an amazing amount of gravity assist. We went by Titan 127 times. In fact, I'll show you again in a minute. And we got over 30,000 meters per second of gravity assist delta V. Carried 3,000 meters per second of chemical fuel, and Titan provided 30,000 meters per second. So without Titan, we wouldn't have been able to do this mission. One of the things with the Huygens probe, this mission, by the way, I love the word choreograph when Larry introduced it, because it was highly choreographed. This was minute by minute by minute, because every instrument was body fixed mounted on the spacecraft. So if the cameras were pointing to take that picture, that meant that we couldn't be talking to the Earth. So every minute of the time of these orbits was set up to do some sort of science and then come back and relay it back to the Earth. One of the very first things that happened was we discovered that the probe, which we were going to go 2 quick flybys, drop the probe, zoom by Titan, and be done with it, was that the receiver couldn't track the Doppler signal all the way down to the bit. So the very first thing that they had to do 4 years before we got to Saturn, actually 2 years before we got to Saturn, we actually had to redo the first 2 orbits and put them into 3 orbits, so that when we dropped the probe, we could go by Titan low and high, so there wasn't much Doppler change. This is done by the navigation team, and those are the really smart people. I take off my hat to the navigation team. So we actually did probe separation on Christmas Eve 2004. Was one of the best Christmases of my life. Cut the probe loose, and then 17 days later, we tracked the probe down. So the probe came in like this saucer, and came in, the ablative material is to burn off, dropped a little parachute, dropped the second parachute, pulled off here, then the heat shield dropped off, and then it slowed down and then it took about 15 minutes coming down on the third parachute and surface impact. I'm just going to show you a picture of, this was the probe that was dropped. This was a picture of a engineering model of the probe that was dropped over Iceland. And I will leave it to Conor to tell you about the wonderful science that they got. So one of the things that was kind of unique about Cassini is, it's a 29-year orbit. It goes, so 1 Earth year is 29 years, or 1 Saturn year is 29 Earth years. There we go. It's late for me. It's really early. I'm Pasadena time. So the Prime mission was designed between 2004 and 2008, and we got to close to 2008, and we had a perfect spacecraft. Nothing bad had happened. We had lots of fuel. We were doing great work. So the very first thing we did was ask NASA for a 2-year mission. Typically, you get extended in 2-year, 2-year, 2-year. And so we asked them for a 2-year mission because of some great discoveries on Enceladus that the scientists will tell you about in a minute. And so we went back to Enceladus several times between 2008 and 2010. But in 2009, the scientists said, with the way Cassini's mission works, it doesn't make any sense to go 2 years, 2 years, 2 years, 2 years. So we're going to ask for a 7-year extension. We're going to ask to go all the way to 2017. We're going to get a whole nother season on Saturn, and then we're going to end it. And so that's the way this whole mission was designed. Now, we did have to go back to NASA headquarters every few minutes or every couple of years. It seems like we were doing senior reports a lot. To tell them we were doing good, the science was still worth it, everything was doing great. But that's one of the unique things about Cassini was that 7-year extension instead of the normal 2 years, 2 years, 2 years, 2 years. And then the end. And so this is, Phil asked me to particularly put this in. I think it's in 2 or 3 of the other talks. But so kind of to summarize what I've been trying to tell you is we went in the northern winter season. We made it through all the way through spring in the equinox time. And then we got into the summer season. So we got in at the end of winter and made it to the beginning of summer. And that was very important for the science. And I think that was part of the revolution. Plus, it just took it takes a long time to put your story together. So again, 2004 to 2008, we did 127 flybys total. There were 47, I think, original Titans, and there was only these 3 Enceladus flybys. We were going to fly by this dead icy moon 2 or 3 times, image it, and get out of there. And of course, between 2006 and 2007, they started putting together the story that there was really some neat stuff on Enceladus, and so we needed to go back. So we added all of these Enceladus flybys. We actually had 23. We went by from 1,000 kilometers by to closest approach all the way down to about 100 kilometers at the end, actually about 50. And we caught some of the other icy satellites and other flybys. But this, again, this was our engine. Every time we flew by Titan, we were getting between 800 and 1,000 meters per second of speed up to shape the orbits, to shape all of the orbits around. So if you put that all together, it looks like this. And I promise I won't play this too long because it makes me seasick, so I must do that to you. But if you can see the tie points, that's the Titan orbit. So those are the tie points coming. So you can see how every single orbit was shaped by flying by Titan in a particular time, in a particular angle. And we used all of our chemical propellant to really just shape to get to Titan the right time, right place, right angle for the next shaping orbit, which is another reason why this was such a unique mission. Most of the spacecraft go into orbit around another planet, and then they just go into orbit and orbit and orbit and orbit. And then we did the F-rings, and then we did the inside the rings. So that's the last 9 months of Cassini's life. From November 2016 to September 2017 was this 20 orbits outside the F-rings, the yellow, and then 22 orbits inside the orange. We'd studied this for a long time, but we really didn't know how that would work. You know, we didn't have any feel. I mean, we did. We studied and studied and studied. We had the best Saturn experts in the world, and we were trying to hit just a really narrow corridor in there. So we did 42 orbits of the F-rings, and then 42 short period orbits. And once we went in, so we were trying to fly below the D-ring and not hit any of the dust. So this is the atmosphere or the distance from the center of Titan in kilometers. So this is 65,000 kilometers. So we flew this 20 orbits right around here, and then we got a distant 100,000 kilometer flyby of Titan, and it pushed us from here to here. And then we flew another 22 and then finally got into the capture. And the difference between, this is all ballistic. The only thing that's shaping those orbits was Titan. That was it. And it wasn't very close during that time. So we jumped down here. We had about a 1,200 mile, 2,000 kilometer roughly corridor that we thought was safe. It was below the rings. So we weren't going to hit dust, and it was above the capture atmosphere so that we weren't going to slow down too much and crash before we wanted to. So it looked like this. We kind of had 7 seconds of terror every 6.5 days. I love that picture. And again, there's Earth and Sun in the distance. So every 6.5 days, we did this 22 times, and got some of the most amazing outside-in pictures of Saturn that I think will be done in my lifetime anyway. Looking at it from a different voice, so this is the final day. This is the last day of Cassini. This is November 14th to 15th, 2016. And you may realize that we all talked to the Deep Space Network. So we talked to Goldstone, we talked to Madrid, and we talked to Canberra. So as the Earth turns, you can always be in view of a spacecraft, or the spacecraft can always be in view of the Earth. So we're relaying the data back over Goldstone, and then Canberra comes into view. We're relaying the data, and now Canberra is the only thing that can see us. Canberra, if I did it correctly. And we're coming down, and Canberra is catching us at the end. So, boy, I hit 25 minutes. So this is it. This was 13 years of Saturn, color-coded by year. This was the 2004, the big swings, and all the way into the end. And there's our logo. You can go more into more of that. And this is the end of mission. Okay? You guys want? Do you want the green? Okay.
So our next speaker is Professor Philip Nicholson, who is a professor of astronomy and acting director of the Center for Astrophysics and Planetary Science at Cornell University. He is a member of the Visual Infrared Mapping Spectrometer Science team on the Cassini mission, and previously he led the Cornell Caltech team studying the impact of comet Shoemaker-Levy 9 into Jupiter using a Hale telescope. Phil's research centers on two main areas: the orbital dynamics of planetary ring systems and natural satellites and infrared observational studies of planets, their satellites, and their rings. Please welcome Professor Philip Nicholson.
Good. Here we go. Good. Whoop. A little loud. Oh, double. So Julie cheated a little bit. Only on this picture. She said she wouldn't show any science, and then she showed the best picture. But it's been shown a lot of times. It appeared on the front cover of National Geographic. I forget which year, but it's got lots of airtime. Nevertheless, it's an absolutely gorgeous picture, so it's always worth showing again. As Julie said, this is a backlit picture. The sun is actually here. Actually, the sun is here. You're seeing the refracted image of the sun bent around by the atmosphere. So the sun is behind the planet, and that's the only time we can look at the sun in the mission. Julie, well, maybe not Julie, but the project in general frowned upon us pointing the cameras and the infrared instruments at the sun directly. So we could only look towards the sun during times like this when the sun was eclipsed conveniently by Saturn. But scientifically, the nice thing, as Julie said, is that you get to see these outer components of the rings. This is the E ring. This is the G ring here. The F ring is actually this very bright one here, and then the D ring is in here. None of those rings can you see very easily under normal conditions. They're tenuous, low optical depth rings. They don't reflect light very well compared to the other rings. So we did this several times in the mission, but this was the best mosaic we got. So the history goes back a little bit before Voyager, just in terms of the naming of the spacecraft. And as Julie mentioned already, the orbiter was named after Cassini, and you can see he's either Jean-Dominique or Giovanni Domenico, depending on which you take. He's actually Italian, who became the first French astronomer royal. So this is the French Paris Observatory in the background. He didn't discover Saturn. Of course, that was known to the ancient Greeks, but he did discover two of the large moons. Actually, his friend Christian Huygens in Holland had already discovered Titan, but Cassini discovered Iapetus and Rhea in 1677. Huygens discovered Titan, but for those of us that study the rings, he's most famous because of a book he published which explained the peculiar appearance of Saturn, why it had ears on either side, and why the ears would disappear every 15 years. And he explained this as a ring system, a flat ring system around Saturn, and as Saturn moved around the sun and changed its appearance to the Earth, we would see the rings and then not see the rings. So he was the first to explain what we were looking at. Just an overview, these are actually all Voyager images of the outer planets, just to put them to scale. So here's Jupiter with its banding, the great red spot. Here's Saturn. Looks much more bland. It's not nearly as colorful, and the clouds are not as discrete and as obvious as they are in Jupiter. Nevertheless, there are bands, and the rings, of course. Compared to these two planets, which are pretty similar in size, Uranus and Neptune are quite a bit smaller, but then, of course, the Earth is much smaller again. So I'm going to say a few words about the context of the giant planets, just one or two slides. Then I'll talk about Saturn, about the atmosphere, some of the things we've learned about that. And then we'll wind up talking about the rings, which, of course, is the best thing that Cassini did. And I'm going to leave out the satellites because other people will talk about them. So this is just a slide from my introductory astronomy class to remind people of the sizes. So this is the Jovian or giant planets, Jupiter, Saturn, Uranus, and Neptune. Here's their radius in kilometers, or I like to think of it just in Earth radii. Jupiter is about 11, Saturn is 9.5, Uranus is 4, and Neptune is a little under 4. In terms of masses, though, that's another way to look at them. Most of the mass of the solar system, except what's in the sun, of course, is in the giant planets. So Jupiter is about 300 Earth masses, Saturn a bit under 100, Uranus and Neptune are each roughly 15. So while they're very massive, they're surprisingly low density. For comparison, the density of the Earth is about 5.5 on average grams per cc, or 5,500 kilograms per cubic meter. The terrestrial planets, Mars, Mercury, Venus, and Earth, all range between 3.9 and 5.5. All the giant planets are much less. Saturn is the least dense at 0.69. So what's often said in elementary textbooks is that if you could find a big enough bucket of water, Saturn would float if you were to dump it in the bucket. It's less dense than water. Jupiter is a bit denser, about 1.3. Uranus and Neptune are similar. This tells you that they must be made of intrinsically light, low-density material. And the fact that they're so massive means that gravity will tend to compress them in the center. That means they need to be made of even lighter stuff than you might guess by just looking at these numbers. You might think Jupiter is made of ice, given this density of 1. But in fact, to make a planet as big as Jupiter and be that low density, it has to be mostly hydrogen and helium. So these are schematic models of Jupiter and Saturn. If they have cores, and we don't know for sure whether, we're pretty sure Saturn has a core, Jupiter is still unclear, but if they have any rock and icy material, the stuff that makes up the terrestrial planets and Uranus and Neptune, it's in a fairly small core in the middle. Most of the planet is hydrogen, helium. Most of Jupiter, the hydrogen actually is in a metallic state. The pressure is high enough that the electrons are stripped off the hydrogen molecules and they can freely travel around, which means it is electrically and thermally conducting. This is the source of Jupiter's very strong magnetic field. We think it's generated in this metallic region. Then there's a skin of molecular hydrogen and helium on the outside. Saturn is just a smaller model of this, but because its mass is less, its gravity is less, so the hydrogen is confined to about the center half. We've actually measured the gravity of Saturn on the last few orbits, and we've measured Jupiter recently with the Juno spacecraft, so these models are in the process of being sort of reworked and re-engineered at the moment. Okay, enough about background. Let's talk about the Saturn itself, and in particular the visible thing that you can see, which is the atmosphere. So as you might have already inferred from here, there is no solid surface on either of these planets. It's a molecular hydrogen, very thick. This is really too thick to call an atmosphere. It's sort of an envelope. And then there's a transition where you go to metallic hydrogen, but the temperature here is already almost 7,000 degrees Kelvin in Jupiter, and maybe 6,000 in Saturn. It's well above the melting temperature. So none of this is solid. This just grades from gas into what you might call liquid, but it's above the critical point as well. So there's not even any sharp boundary between the gas and the liquid. It just gets denser and denser and hotter and hotter. Any solid stuff is way down here if it exists. So there is no solid surface to be seen on these planets. All you see is clouds when you look at them from the outside, no matter what wavelength you use. Some wavelengths you can see deeper in the clouds. Juno is looking down to about 100 bars, 100 times Earth atmosphere, by using a microwave instrument to look at several centimeter wavelength coming out. Cassini doesn't have one of those. We're looking in the visible and infrared and ultraviolet. So we look in the top part of the atmosphere, the part where the pressure is similar to what it is on the Earth. And as you saw before, Saturn, the cloud banding is pretty faint. Apparently it has an upper atmosphere that has some hazes in it that tend to scatter light, plus the cloud deck is a bit deeper on Saturn than it is on Jupiter. This is a view taken 2 different years, but both of these were in the early part of the mission. As Julie said, we arrived near the northern winter, or what I like to think of being Australian as the southern summer on Saturn. So when we first arrived, the sun was illuminating the southern hemisphere and the south side of the rings, but the spacecraft, of course, flew from the north to the south and was able to look down on the dark hemisphere, which we can never do from the Earth. So the spacecraft was able to get images like this of the northern hemisphere of Saturn while the sun was shining on the bottom. And what you see immediately is how different the rings look. This tells you immediately, without doing any quantitative stuff, that the rings are quite opaque. In particular, the B ring here, which is the ring that's brightest under normal solar conditions. That's what you see in a telescope when you look at Saturn's rings. You see the B ring and the A ring. The B ring is almost black when you look at it from the other side. It lets almost no light through it. The A ring lets a bit more light through, and the C ring, which you can barely see here, it's actually just inside there. You can see it where it crosses the planet, just there. It actually is this region here. It's relatively bright. So you can think of it as like a gauze curtain. It doesn't block much light, doesn't reflect much, but if you have light shining through it from the other side, it scatters quite a bit of light, and you can see it. Or like looking into a fog bank or something with a headlight behind you. One other neat thing you could see here a bit better is these things, which Jupiter doesn't have. These are the shadows that the rings cast on the planet, and these are amazing. The geometry keeps changing as the elevation of the sun changes. It's incredibly complicated and interesting. If you lived on Saturn, if you could do that, not only would you have day and night to deal with, you'd have ring shadow to deal with. It would be a very complicated pattern of sunrise and sunset and light and dark. This is an image of Saturn, not in the visible, but in the infrared. So this was taken with the instrument I work on, and Bonnie, which is the infrared mapping spectrometer. So this is an observation taken in the 2 to 5 micron range in the near infrared. This was taken, unlike the previous pictures, with the spacecraft basically right in the plane of the rings. So the rings are edge on. They're just this thin blue line across here that's basically just 1 pixel wide. But here's the sunlit side of the planet. The sun is over here. In the infrared, we can see the back side of the planet, the dark side, which you can't in the visible. There's no light to be reflected. What we're seeing here is thermal radiation coming up from the deep interior. The deeper you go in Saturn, the warmer it gets. There is a point well below the clouds where the temperature is like room temperature in this room, 300 or 400 degrees Kelvin. And that produces a lot of black body radiation, and that comes up and sort of filters its way through the thin parts in the clouds, and we see it. So wherever you see bright red here, that means the clouds are pretty thin, and that radiation is coming out unimpeded, and the black regions are where the clouds are thicker. This turned out to be a very good way of mapping the clouds on the planet. You can see the clouds more easily here than in the reflected sunlight. Looks more like Jupiter in the infrared. Interesting, again, you see the shadow. So where the rings shadow the planet, you don't see any sunlight, and again, you see the thermal emission. From my point of view, not being an atmospheric scientist and not getting into all the details, the things that were really amazing at Saturn were the polar regions. And initially, the South Pole was kind of interesting. It was the only pole that was in sunlight, so this is an early visual image. And this is the South Pole right here. And there's an interesting looking vortex pattern and several different layers of clouds. These are actual shadows being cast by the upper clouds on the lower ones. So this is one of the few places where you get a visual impression that the clouds are at multiple elevations. Normally, just looking down from on top, you can't tell. but in this picture with the shadows, you see it. I can't really explain what this is, and we don't have an atmospheric person here. We know a bit more about the North Polar region, but it looks vaguely like a hurricane, but it's not physically very similar to a hurricane. It looks a bit like an eye of a hurricane to a non-expert. This is the North Pole, and when we first arrived, it was in the darkness. It was the northern winter, so there was no sunlight on it. So this, again, is an infrared image taken at 5 microns. So again, the red is the thermal radiation coming out of the interior. Here's some bright sunlight being scattered by the edge of the planet, but notice this thing here. And then the pole is right here in the middle. And here is another view looking a little more down on the pole, and here the pole is here, but again you can see this sort of hexagonal shaped thing. So this was one of Cassini's first discoveries that was kept secret for a long time. It's the large nut that actually keeps the planet together and stops it just falling apart. It's where it's been sort of screwed down. Really, we don't quite understand this. It looks again a bit like a hurricane, but actually it's not. We think this is a bit analogous to the jet streams on the Earth, but rather more organized than the jet streams on the Earth, which look rather more curvy and rather chaotic. Interestingly, this blue is at a different wavelength. This is 3.5 microns, and that's where hydrogen emits when you hit it with electrons. So this is the North Polar Aurora on Saturn. Saturn has aurora like the Earth and Jupiter. You see them mostly in the ultraviolet, and I'll show you a UV image in a bit, but this is an infrared picture of the aurora. And then finally, this is just another view of the vortex, which is so wonderful. So here's this North Polar vortex. You see the hexagon a bit better. These are measurements of the wind speed going around here at different latitudes. And you can't really see the scale, but the hexagon here is about 78 degrees latitude. There are circles here at 70 and 80 degrees latitude. And this is the wind speeds measured from tracking clouds versus latitude. So this is the pole. So there's a big raceway of high-speed winds that run around where the hexagon is at about 78 degrees. They get up to 120 meters per second. That's about 250 miles an hour relative to the interior of the planet. But also when you get right near the center, the winds again get up to about 120 meters per second before dropping precipitously to 0 right at the pole. So I'm told that this is a classic picture for a vortex on the Earth, except most vortices are much, much smaller. But think of the vortices produced by big planes when they take off from airports or something. This is a much giant version. On the very last orbits of the mission, we tried to do several different things we couldn't do before. And the atmospheric people were asked to come up with something they would do. And they said, well, we could do a complete strip from the North Pole to the equator on these final orbits and stitch them together. And this is what they did. So this is a series of images taken by the camera in the visible. This is a similar series of spectra taken by the infrared instrument. So this is the North Pole. That's that hole right at the North Pole. And this ends up almost at the equator. And you can see as we got closer and closer to the planet, the field of view got smaller and smaller. And there's a movie being made of this that you can see online that's really quite incredible. The amount of detail to see in the clouds here is amazing. It's about 10 times better resolution than we saw in the rest of the mission. As I said, away from the poles, there isn't so much going on Saturn, but there are some isolated storms. This was the biggest one that was seen. We were lucky to see this one. It blew up in 2010 and lasted for about a year. It started here and then spread around this latitude, and by the time it was finished, it had spread all the way around the planet. This is the visible view. This is an infrared view. And here's a mosaic. So this is stitched together. This is the whole 360 degrees, so a strip. Taken, well, we spent there sitting there for 10 hours watching the planet rotate to get a full mosaic. So this is when this cloud pattern had managed to go almost all the way around the planet. And this is a blow up of the head region. And the reason to show this, other than the interesting looking swirls, it looks a bit like some pictures you've seen of Jupiter clouds. Notice this little blue spot here. And a short time later, another mosaic, a partial mosaic was taken of the same region. So I'm not sure how much later, 30 minutes later. And you see this feature again here, but the blue spot is gone. And you might think it's just an artifact, but it's not. It's real. And what we think this was a lightning flash, a lightning stroke that just by chance happened while the shutter was open. It supported the view that already the atmospheric scientists had, is that what you're looking at here is something analogous to a giant thunderstorm outburst on the Earth. And not surprisingly, you might be lightning connected to that. I mentioned you can see the aurora in the ultraviolet as well. This is my one picture that's not a Cassini image. Cassini did not have an ultraviolet camera, so it got data on the ultraviolet aurora, but spectra, not really beautiful pictures. But Hubble Space Telescope is capable of taking pictures in the ultraviolet. So this is a Hubble image of Saturn it's a visible image with an ultraviolet image of the aurora stuck on top with Photoshop. But it's a real image taken by Hubble and put together, so it's spectacular. The magnetic pole is right here. It's the same place where the spin pole is. So enough for Saturn. We'll talk about the rings for a little bit. And this one is a lot of color pictures you see from spacecraft, especially Voyager ones, tend to be false color images. For one thing, the cameras didn't cover the whole spectrum. The Voyager cameras were not really sensitive in the red at all. They were sensitive in the blue and the UV. But a lot of things in the outer solar system don't have a lot of color to them. They're fairly white and pale. But this is an attempt to make what we think is close to a true color image of the rings. So if you were actually on a spacecraft and out there looking at the rings, you would see something like this. They're kind of a yellowish tan color. This is the A ring, the B ring, and the C ring. The gap in between is known as the Cassini division, named after Cassini, because one other thing he discovered was not just one ring, as Huygens had seen, but two rings, the A and B rings. This is the F ring out here. I said your F ring was hard to see normally. It's just barely visible. Here's a gap called the Encke gap. We'll come back to this in a minute. This is kind of cute. Julie mentioned that once we got our first extended mission for 2 years, one of the arguments we made for that was that in 2009, the sun would go from the southern hemisphere to the northern hemisphere. So it would be the equivalent of the equinox. It would be Saturn's version of March 21st, except that only happens every 29 years on Saturn. And that was interesting from a seasonal point of view. The atmosphere people and the Titan people said, okay, we'd love to see the northern summer now that we've seen the northern winter. The ring people said, oh, that's interesting. We can see the rings with the sun shining on them edge on. I wonder what we'll see. I'll show you some more pictures in a minute, but something we weren't really thinking about was that the moons cast these bizarre shadows. So this is the shadow of Mimas, which is slightly inclined. It's on an orbit that's 1 degree out of the plane of the rings. So when the sun is very close but not quite edge on, Mimas can actually cast these very long, skinny shadows across the rings. This is an earlier version of that mosaic that I started the talk with. This is one of these images where the sun is behind Saturn, so we're able to look back at the sun. And that let us highlight the E ring out here. And right here, do I have this right, Bonnie? I think it is. So Terry will talk about this later, so I'm not allowed to say what the satellite is, but its name starts with E. And we believe now it's actually the source of the E ring. We didn't know that before Cassini. The G ring is much fainter and harder to see here. The F ring, though, is quite bright. It's this narrow, detached feature. And this whole inner region, if you look back at one of those earlier images in sunlight, you would not have seen anything here. That's the D ring, and it is so transparent that you don't see it under normal conditions. This is an infrared view of the same region. So you're looking at the backside of the planet, again showing O, B, and C, and then the F ring out here. Infrared people like to show pictures of wiggly lines, but we always get told, why do you guys show these meaningless pictures of wiggly lines? But I was told there would be some scientists in the audience tonight, so I figured at least one set of wiggly lines was okay. So these are actually spectra taken by the VIMS instrument of the rings from 1 to 5 microns, which is the range our instrument covers. And they all look fairly similar in shape. The different colors indicate different parts of the ring, ranging from the F ring, A ring, B ring, through C ring. But actually, except for absolute brightness, they all look roughly similar. They all have these strong absorption bands here at 1.5, here at 2 microns, and a very strong absorption band at 3 microns. These are all characteristic of water ice in any of its various forms, either snow or solid ice. But actually, from the shapes of these bands, we know it's not a solid sheet surface. It's not like looking at a skating rink or something like that. We're looking at something more like snow. The particle sizes are sort of between 20 and 50 microns. Now, we know the particles in the rings are centimeters to meters in size. So this is not the individual particles orbiting in the rings. This must be the texture of the snow or ice, the frost that's on the surface of the ring particles. So we know the sizes. One of the things we had hoped to do with VIMS, of course, was measure the other things that were in the rings other than water ice. We had seen from ground-based telescopes that the rings had water ice in them. Disappointingly, they're basically pure ice. There's nothing else in this spectrum that you can't explain with ice. We're still wondering what else might be there, but anything else is there is way under 1% in composition. They're almost pure ice, which itself is a puzzle. If you look at images of the A-ring at reasonable resolution, you see lots of these things. You see these funny-looking things that look like sets of concentric circles when you look down on them. They're actually waves that are propagating in the rings. This is an occultation measurement of the same region. Here VIMS observed a bright star going behind the rings. So we measured the density of the rings, how much starlight was broken. So what you see here is transmission through the rings. So these alternations in brightness are in fact alternations in the opacity or the optical thickness of the rings. And it turns out that this one is what we call a density wave. It's a wave that is a little bit like a sound wave. It's a series of compressions and then rarefactions of the ring. It's actually controlled by gravity, so it doesn't work the same as a sound wave, in which pressure is the important thing, but it looks rather like a sound wave in that there are alternations in density. And they propagate outwards across the rings. This one turns out to be different. It propagates inwards. This is a vertical wave. This is if you took a rug here and shook the rug vertically, or had a slinky and shook it and let the slinky propagate waves down the line. So we call this a bending wave or a vertical wave, two different kinds of waves. They were predicted theoretically. They were first studied in galaxies, and they were, in the early days, this was a theory for the spiral structure in galaxies. In fact, it turns out these are not concentric circles. They are extremely tightly wrapped spiral patterns. So each of these is a four-armed spiral. So every fourth bright peak is the same feature wrapped 360 degrees around again and come back. Incredibly tightly wrapped. Just like galaxies, but galaxies are much less tightly wrapped. Here's another view, an optical image of one of these density waves. And this is an attempt to give you an idea what it would look like, but not to scale. So this is that same wave. So it has 4 arms. This one has 6 arms. So there's 6 sources here. And if you follow this around, there are 6 spiral arms here. But to make this image visible, we basically expanded the radius scale by factors of many thousands compared to the true rate. I mean, in reality, this is all compressed into a very narrow radial range. These turn out to be very useful tools. It turns out the wavelength of these waves is a direct measurement of how much mass density is in the ring. So we know that the A ring is about 40 grams per square centimeter of mass in the rings. That means if you took the rings and squeeze them down to the density of solid ice, they would be 40 centimeters thick. If you want to visualize how much stuff is in the rings, there's about half a meter's worth. In reality, it's spread over about 5 to 10 meters. But if you compressed it all, it's about half a meter. By comparison, the Earth's atmosphere, if you squished it to water density, would be the thickness of, somebody must know? No. The Earth's atmosphere. No scuba divers in the room. No, about 10 meters, about 30 feet. If you squash the Earth, so if you go down 10 meters in the ocean, the pressure doubles compared to the surface pressure. So the rings are 20 times less stuff in them than there is in the Earth's atmosphere. There's not much stuff there. I'm going to skip quickly over these if I can. These waves driven by satellites, these density waves and bending waves, are mostly out here in the A ring, and they turn out to be driven by resonances with the satellites. There are places in the rings where the orbital period of the ring particle is a rational multiple of the period of the satellite. So this particular one is at the 5 to 6 resonance with the satellite Janus. That means the ring particle orbital periods are 5/6 of Janus's period. So it's the satellites that are actually driving these waves. I'm sorry, I neglected to say that. This is another example of a Janus wave. But it turns out in the C ring in here, there are also some waves, but you don't see them at normal resolution. This is again another one of these occultation profiles, watching a star go behind the rings. And if you blow up this region, you see this, and you begin to see a couple of these things that look like noise spikes actually turn out to be little multiple jiggles. And then if you take this one and blow it up even more, you can see it's really a nice wave. And it turns out to be like those bending waves in the rings, except there are no satellite resonances here. And we wondered about what these were, but it turned out some very clever people back in the 90s had guessed this. A couple of these were seen in the Voyager data, but not well understood. And what we think they're due to are oscillations inside Saturn. So it's analogous, we call this chronoseismology in the hope that people would think of it as analogous to terrestrial seismology, but better still, analogous to helioseismology. The sun oscillates in all sorts of different modes, presumably triggered by convection in the interior. We think this is a similar thing. There are modes oscillating inside Saturn. This just shows you cartoons of what some of the low-order modes might look like. The ones that generate things in the rings are these ones down the diagonal, the ones where you have sort of orange slices, and the white and dark represent regions of higher and lower density. And as they rotate, they produce a rotating periodic term in the gravitational field, and that's what looks to the rings just like a satellite perturbing them, and it drives waves just like the satellites do. But we're in the process of understanding these things, and in the end, it's going to tell us quite a lot about the interior of the planet. But I can't tell you what. But there's a whole bunch of these, and we've been able to identify how many arms are in the spiral pattern. So some of them are 3-armed, some of them are 4-armed, some of them are 2-armed, but the biggest we found is a 10-armed one. And this is all by putting different occultations together. So getting near the end now. So we've mentioned already a few times that you could look at the rings when the sun was edge on, so we thought this would be interesting. So this is such an image. This was taken in August 2009. What is strange about this picture compared to the ones I showed you before? This is a visible image. It's not infrared or anything like that, and the sun obviously is over to the left here somewhere. Notice the rings are much brighter here. This is the lit side, well, sort of. Yeah, the rings are almost edge on to the sun, but kind of this is the lit side. Rings are much brighter here than over here. Why? The answer is you're not really seeing them in sunlight. The sun is so close to edge on, it's hardly illuminating the rings. What you're seeing is the rings shining in Saturn shine. So this is like looking at the dark side of the moon and seeing it illuminated by reflected light from the Earth, which you can see under new moon conditions. So this is the rings shining by Saturn. Saturn is very big if you were standing here on the rings. It's not like the moon and the Earth. Saturn fills half the sky from the rings' point of view. But you see some other really neat things in this geometry when the sun is edge on. So this is the edge of the B ring right here. Sun was coming in from this direction. And there's all this weird bright structure here. This is some kind of vertical structure. We loosely refer to these as the B ring mountains because that's what they look like. But really, we don't know what they are. The main rings are about 10 meters thick. These mountains are actually casting shadows that are a bit hard to see here. But from the length of the shadows and the geometry, we know these are about 1 kilometer high. So these are 1 kilometer size, some sort of irregular vertical structure in the rings that we never suspected before. This is the outer edge of the A ring, and here the edge of the ring doesn't do anything, but there's a gap here called the Keeler gap, and the edge of the Keeler gap also has vertical structure, and you can see the mountains casting shadows. This is one of the small satellites in the ring, Daphnis, and actually it's big enough, it's much thicker than the ring is. It's a few kilometers in size, so it also casts a nice shadow. So you see quite a bit of this. These are, the ones outlined in green are these bending waves in the outer A ring. The other ones are density waves, most of these other features. The bending waves, since they involve material being displaced up and down vertically out of the rings, that's like flying over a country when the countryside with shallow undulations at sunset, and the very low sun angle picks up undulations. Those of you that have flown and landed in Rochester have seen the drumlins up there. Absolutely wonderful if you see them close to sunset. So these bright features here are in fact these bending waves. These are 2 of the bending waves, highlighted by the edge on. Again, here's Daphnis casting its shadow. So I want to end saying a little bit about perturbations on these edges. That's something else that we quite understand. What we know is that the outer edge of the A ring here, we've known for a long time, even since Voyager, that this is near the 7-6 resonance with Janus. So it's at the point where the orbital period is 6/7 of Janus. And theoretically, a theory was developed in the 70s to say that that interaction between Janus and the rings through the resonance could actually exert a force on the rings. And essentially, the satellite acting at a distance pushes on the rings. It really pushes it by generating waves in the rings, and momentum gets transferred from the satellite, actually from the rings to the satellite. So it's paradoxical. It's gravity, but but it acts like a repulsive force at the resonance. So we think that actually keeps the edge of the ring where it is. That's why it's so sharp. And the prediction from that, which was never testable by Voyager, was that if that was real, you would expect to see a perturbation on that edge that would have 7 lobes in it. There would be a 7-lobed oscillation around the ring. And lo and behold, Cassini saw that. So there's about 200 images that went into this, a lot of data. This is about 15 hours of observation, which is about 1 orbital period of the A-ring edge. We just sat there with the camera, looked at the ring, and then let the ring orbit through the field of view so that we could build up a 360-degree mosaic. And this mosaic has been stretched the bejesus out of in the vertical direction compared to this direction. So this is all the way around the rings. This is about 1 million kilometers. This is 300 kilometers from here to here. But 1, 2, 3, 4, 5, 6, 7. So it's just beautiful. They're a little bit irregular, but this is the resonance showing itself in the real world. And so the resonance is really there. It probably really is confining the rings. There are some little satellites in the rings, and Bonnie will show you some pictures of the actual objects. But the Encke gap and the Keeler gap in the outer A-ring each have a little satellite in them. Here's Daphnis, one in the Keeler gap, and it produces these little perturbations on the edge. Now, these are not resonances because we're quite close to the satellite, but this is because, here's the geometry. Here's ring particles. The ones inside the gap, following Kepler's third law, are orbiting faster than Pan, so they move by Pan slightly faster, and as they move by, they get a little gravitational kick from Pan, so they get little eccentricities in their orbits, so they start wiggling. So this is one orbit, and gradually the wiggles damp out and die away. Similarly, the particles on the outside edge of the gap are traveling more slowly than Pan, so relative to absolute terms, they're going this way. Relative to Pan, they're moving backwards. So you see the wiggles going this way on the inside edge and this way on the outside, and you see this just beautifully here with Daphnis. But you can see that there are perturbations that should extend inwards from the ring, and Cassini took this wonderful image on that first orbit insertion that Julie talked about. So Pan is off here. This is the Encke gap. This is a very edge-on image. It's kind of foreshortened. But you see, this is the wake produced by Pan, perturbing in. Think of this as a wake like the speedboat wake produced by a speedboat going by, except in this case, it's gravity that's doing it. So finish up with, so this is I'm stealing this one from Bonnie, but it's just too beautiful not to show. So this is a Cassini image right near the end of the mission when we got very close to the rings. We knew Daphnis was there. All the previous pictures, it was just basically 1 pixel or 2 pixels. And now we actually get to see Daphnis, but now you get this absolutely gorgeous image. The image was taken to show Daphnis, but we took a mosaic and it just shows this wave pattern on, in this case, this is the outer edge. This is the outer edge of the ring, so this is the outer edge of the gap. And again, the red arrow shows the relative direction of the ring particles that are moving. Just beautiful. This gap is 37 kilometers wide. And finally, this is almost the last, maybe the last image Cassini took. Do you know if that's really the case, Julie? I think it is. And Vims was able to take it. As we were coming in on Julie's movie, if you remember it, we came in from the back side of Saturn and then flew quickly over the front side and then down and out again. And on the very final orbit, this was an image of, we targeted the region in the clouds of Jupiter where we think that Cassini was going to dive in about an hour or two later. So this is the last image, and it's intended to show what we think was the target place. And then as you know, the spacecraft was then deliberately flown into the atmosphere to sort of tie it up nicely and end the mission, but it was basically out of fuel at this point. And we took data right up to the very end. As you can see, the antenna was pointed, Earth-pointed during the entry into the atmosphere. So we were sending back in situ data on the chemical composition of the atmosphere and the magnetic field right up until the last few minutes of the mission. So these engineers did a great job. It's just amazing. I might say after 13 years, the signal disappeared within a few seconds, I think, of when Julie and company told us it was going to go. It was kind of sad, but at the same time, it was a beautiful piece of engineering work at the end.
Okay. Our next speaker is Dr. Bonnie Buratti, a principal scientist and technical manager at NASA's Jet Propulsion Laboratory, who has expertise on the structure and evolution of icy moons and other small bodies. She is currently serving on the science teams for both Cassini and the New Horizons missions, and she is also the NASA project scientist for the Rosetta mission. Please welcome Bonnie Buratti.
Thank you so much, and thank you for coming. I want to remind everyone that everything we're showing is your heritage. I mean, we did this for you. We did this on the taxpayers' dollars, but, go to our website, which I have at the end, or even go to the planetary data system, and it's all your data, so just enjoy. So Saturn has 62 moons, but we're only going to be able to talk about a few of them tonight. Two of the special ones, Enceladus and Titan, are going to be talked about by my colleagues. So just to summarize what I'm going to talk about, and I'm just picking a few of my favorites. I'm not even going over most of them, or all the important ones. So first of all, Pan. This is this object that is in one of the gaps, the Encke division in the A ring. Daphnis, which Phil already showed you that spectacular image in the Keeler gap. Atlas and Prometheus, which are two of these sculpting of what we used to call shepherd satellites. And then some more garden variety, but they're not really garden variety moons, Tethys. They're garden variety in the sense that they're regular, they're at least round. Dione. I'm going to skip Rhea because there are just too many things to talk about. And then getting on to Hyperion, Iapetus, and Phoebe. Okay, so for the third time, I'm going to show this graphic here. It's really quite key because it really shows you the whole mission in a nutshell. Not only are this huge number, 127 flybys of Titan, but Enceladus was the second most studied moon. But I'm going to focus here on these guys down here, which I call the weirdest planets in the solar system. You notice that calling it a planet is sort of a dig on the people, the International Astronomical Union, which demoted Pluto as a planet, because we don't, as astronomers, we don't think of planets, whether something's a planet or not. I mean, we call Titan a planet in our weak moments. So, these things are all fully planets, and I'll tell you, Pluto is way more than something that isn't a planet. That's a whole other talk, but it's pretty spectacular. So there's right at the end of the mission, we managed to get, which is kind of a whole new mission. Oops, now I goofed up here. Yeah, a whole new mission of what we called 5 fabulous flybys of Saturn's ring moons. Phil already talked about the fact that Saturn has this unique family of moons that are associated with the rings, and at the end of the mission, we got these spectacular flybys, and I'll talk about them briefly at the end. Okay, so Julie showed this picture of Phoebe, and I first began my career as a planetary astronomer on the Voyager mission. Here is Voyager's best image. This is more than 1 million miles away. And this spectacular image of this captured Kuiper Belt object from the outer reaches of deep space beyond the orbit of Pluto. And if you get closer, there's one of the craters. The boulders, the smallest boulders you can see on there are about the size of a football field. So this mission brought us up close and personal to these moons. Now, there's another thing about Phoebe, and we were all thinking it as we entered Saturn orbit insertion, but we never talked about it. And that is that we observed Phoebe before we actually went into orbit around Saturn. And if the whole mission had failed, then at least we would have gotten this flyby. We also got some good images of Titan before we went into orbit. But lo and behold, we were successful. This is Dave Seal's rendition. Dave Seal was actually the mission manager, one of the first mission managers on Cassini. He's also a space artist, and this is a famous, I mean, it's all over the internet, image that Dave put together of an artist's rendition of what it looked like when Cassini was entering Saturn orbit. Now, I want to first talk about Iapetus, and the reason I want to talk about it is because it really is one of the major, it historically has been one of the major mysteries of planetary science. Phil had mentioned that it was discovered by Cassini, and immediately after he observed Iapetus, he realized that one half was as dark as tar, and then the other half was kind of like a bright icy surface. It might be about as bright as a snowstorm here, maybe about 2 days later. Fresh snow reflects virtually all the light that falls on it, but it gets dirty very quickly. But the fact that this ice here on this moon was quite bright implies that it's fresh. But on this side, this half, it was very dark. Even Cassini realized that, because like the moon, it keeps the same face towards Saturn, like our Earth's moon keeps the same face towards Earth. When Iapetus orbited, it was very dark on one side and then bright on the other. So he knew it was like this yin-yang world. And I wanted to show this picture because I'm a big fan of ground-based observing. And actually, this is some data from David Morrison that was published even before the Voyager images, where he managed to figure out, these are just kind of hand-drawn maps, he figured out, and his team figured out the reflectivity patterns on this moon by just watching how Iapetus orbited as it got bright and dark, and also when it went behind Saturn, the edge of Saturn would like cut back bright and dark areas. He was able to derive these maps, and it is uncannily similar to some of these Voyager, and I think this is Voyager, and I believe these are Cassini, some of these images. He's got the polar caps, he's got this pattern, just to show you how valuable ground-based telescopic observing is, even though we have these spacecraft missions to go to these bodies. Okay, so we got what we call a sneak peek at Iapetus on New Year's Day 2005. This is after the probe. Julie talked about the probe that had been jettisoned that went to Titan. Between that time and when it landed, which was mid-January of 2005. Well, we weren't allowed to do anything on the spacecraft then because it was, here the probe had been jettisoned and it was a European probe, so we couldn't fail the Europeans, and here we were going to go on the surface, so we couldn't do anything. But somebody noticed that we were going to go very close to the orbit of Iapetus, and Iapetus was going to be there. So the scientists, of course, snapped to it and argued that we should look at Iapetus. There's always a tension between engineers and scientists, and this is a very pro-science. We had a very pro-science, engineering team and management, but we did have to fight a little bit, and we finally did get the sneak peek. And this is what we saw, completely dazzling and mind-boggling. We saw this bright part as expected, but look at this, we call it the walnut ridge, this band around the equator of Iapetus. To this day, we still don't quite understand that. The best theory is that Iapetus had a ring and it collapsed. It had its own ring and it collapsed onto the surface. It sounds crazy, but that's the best thing we can think of. So we didn't get our real flyby of Iapetus. We have what we call targeted flybys, and that basically means we expend some of the fuel on the spacecraft to get close to the satellite, usually about 2,000 kilometers away. So in 2007, we did get close to, very close, within less than 2,000 kilometers of Iapetus, and this is what we saw. Now, one of the things that is so weird here is that it's so patchy. We thought that maybe this dust, and I'll tell you where this dust comes from, this dark dust, this stuff that is material that is as dark as tar that is deposited on this moon. We thought that it would kind of get gradually darker and brighter, but you can see that it's very patchy. And the reason, in fact, if we go even closer, see how patchy it is. And that is because once you get a part that is darker or brighter. Now remember, dark things are actually warmer. If you ever step on a pavement, a macadam is much warmer than concrete. Once you get something that is dark, it gets warm, so it tends to cause any ice, this is water ice, that might get on the surface. It causes it to sublimate, and it gets captured on these brighter regions, which are actually colder. So this segregates the frost into different patterns. So here's another example. Now, what causes all this? Okay, so here's a diagram of a giant ring that is around Saturn. Of course, we can't resist, keep showing that image. But here's Saturn and its rings, right in that little dot in there. And Phoebe here is way out. In fact, it's about 13 million kilometers. It's almost a tenth of the distance between the Earth and the Sun. It's about a twelfth of an astronomical unit, the distance between the Earth and the Sun. So there's this giant ring that's caused by Phoebe, dust coming off of Phoebe. And that ring, the dust from that ring spirals in and it hits the side of Iapetus that is in the direction of motion, what we call the ram direction. It just collects all that dust and forms this dark side to Iapetus. And the discovery of this ring actually was not made by the Cassini spacecraft. It was made during the mission by Ann Frobisher and her colleagues, observing with an infrared, the IRAS satellite, and seeing this material in the infrared. But it all put together, again, another example of how you have to use ground-based, or this was actually space-based, it was in orbit around the Earth, use observations other than from the spacecraft. But dust from this giant ring, Saturn's biggest ring, impinges in the ram direction of Iapetus. So here's that ridge way up close. It was another image we got in 2007. It's covered with craters, meaning it's old. As I said, we don't really know. Isn't that amazing? We don't quite understand, how it formed. And this is another oddball. This is Hyperion. We call it the sponge, of course. And this is unusual. It's also covered with Phoebe dust. But here what happens, and I have a little diagram of this, an example of this. What happens is dark material gets into one of the craters, and it is warmer, so it kind of drills down and causes this crater to get deeper. Now this is actually a little picture I took. This is a snowbank in Pennsylvania, and there's cinders, the cinders you put on the road so you don't skid. Each of those little cinders kind of drills down. It's just a physical analogy, drills down into that ice. Okay, so that's what it is happening there. And you can see there's a collision here that almost kind of blew it apart. It's another huge crater. And Hyperion is unusual in that it is, I could say the only, but I can't say the only anymore. Up until about 2015, we knew it to be the only object in the solar system that was in chaotic rotation. Now, most satellites, or all other satellites except for the small moons of Pluto, will either keep the same face towards their primary, like our moon does, or they'll just spin around in simple rotation. Hyperion does neither. It spins erratically, chaotically. And at the time, before the Pluto encounter, we thought it was the only object that did this. The reason it does this is because it's so irregular and it has an elongated orbit. So it gets confused about its spin state and just moves around in this chaotic rotation. 4 of the moons of Pluto are also in chaotic rotation. We just discovered that, but that was in 2015. Okay, so Dione. Let's just move on to Dione. Dione is a very mysterious world. This was the best image by Voyager, and you can see these, what we called wispy streaks, and we thought that they were little, like maybe nitrogen or something, ice, nitrogen-rich ice that got in the surface. But when we got closer with Voyager, we saw, in fact, that it's a bunch of faults. They're just big geologic faults. Here's a good picture showing what it looks like. But the thing that is most mysterious about Dione, and this is one of I would call, be honest, it's a disappointment in the mission. Now, we didn't make all our discoveries right away. We didn't know that Enceladus, which is the next talk, had active plumes right away. It took us about a year. We didn't discover all these mysterious things on these moons right away. Dione, we saw all this evidence that it might be active. There was, first of all, these features over here. This is some work that Paul Schenk did. Those features, they're not craters. Those are some kind of extinct volcanoes. And if you look around here, it looks like some kind of a plume deposit because it's very smooth. It kind of infilled the craters. Here's an image that Roger Clark analyzed back in, I think, the end of 2005. And there's this aura around Dione. There is fields and particles experiments, looking at the magnetic field, looking at like there was something from Dione coming out, perturbing the magnetic field. So there was all this evidence, 7 or 8 pieces of evidence that Dione was active, that it had plumes, and that maybe even had a liquid ocean. One of the things that the next speaker will be talking about is the fact that these liquid oceans may harbor primitive bacterial life. They have all the prerequisites for that. They have energy, they have biological molecules, prebiotic molecules, and they have liquid water. Dione may be such a world. We looked and looked and looked for some really good evidence of activity, like a plume in a photograph. Towards the end of the mission, we really focused on that, but we never found it. We're pretty certain that there's this ocean in the interior that may be similar to that of Enceladus, just to kind of whet your appetite for the next talk. But we never really found, we have to go back and look at Dione better. How about Tethys? Well, here's another example of something we discovered late in the mission. We found these incredibly strange and odd red streaks, just painted. They look like they're painted on the surface. The next image is even better. These red streaks that are just basically painted on the surface. And we have, again, we really don't have any idea what they are. They might be something that is coming out from the interior, maybe a plume, maybe it's not an impact. They seem to be different in composition. They seem to be rich in organics. And if you look at them, they're kind of look like they might be some kind of a tidal or a cracking phenomenon, but it's really ongoing work. We don't have an answer for that. One of the scientists on the mission thinks it's all due to different particle sizes in the material that makes up these streaks. I'm a little suspicious of that, but we're still working on it. And again, these were discovered towards the end of the mission. Now here's another weird thing we saw. Blue pearls on Rhea. This is another thing that Paul Schenk discovered. And again, we have absolutely this is the same image, and this is in a filter, some of the filters that bring out these strange blue features. We think that, again, this might be an example of a ring around Rhea that actually collapsed onto the surface. Now, you might think it's crazy that a moon would have a ring. We think only planets have rings, but there's actually it's actually what's known as a centaur, which is a Kuiper belt object. These are these objects, kind of asteroidal type bodies at the edge of the solar system, out at the orbit of Pluto and beyond. They move into the inner solar system, and one of them, Chiriclo, is its name, actually has a ring. Okay, so it's not so crazy that a moon would have a ring too. So we think that this strange pattern here, that maybe there was an ice-rich ring in the past that Rhea had, and it collapsed onto the surface. That's our best model. So I do want to talk about these ring moons, these crazy ring moons, wild and wonderful ring moons. So at the end of the mission, we were trying to get as many observations as we could, trying to do as much as we could. And a whole new mission kind of popped out where we were able, during this final phase, the F-ring orbits, the 20 orbits that Julie talked about, where we were able to move the spacecraft right up next to the F-ring, right to the edge of the rings. This was before we plunged into the area between the rings and the planet. But we were able to get, actually, we call them 5 fabulous flybys, and they were the best ever observations of the ring moons. These are the moons that either are in the rings or at the edge of the rings. So here is just a summary of these 5 fabulous flybys. These were the dates going from the end of 2016 into April, which was the end of that period, the F-ring orbits. This is right before the dive, what we call the dive-in or the grand finale. So these were closest by at least an order of 2, or a factor of 2, an order of magnitude. And we got some just really odd images. Phil already showed this one, Daphnis. And this was a famous press release image where it shows these wakes. And that was the first, actually, image we got of Daphnis, okay? And that was the first time we were actually able to get a spectrum. As Phil mentioned, we were working on the infrared mapping spectrometer. This is the first time we were able to get a spectrum of dampness. And this led to a model, which I won't bore you about how these objects formed. We believe they formed with the rings, that they started out as a shard, one of the major shards from the rings. And recent evidence is that the rings may be younger than we thought. Okay, but I don't want to get into that too much because science is always driven by disagreement. We don't like, we always disagree. And what is true today? When I went to graduate school, they were formed in the beginning. Now we think they're new. But anyway, these moons are formed from big shards of the ring that kind of accumulated more particles as time went on. So there it is with the wakes. Okay, here is some images of Pandora, and this was a great thing. We were able to get all of the instruments on. All the instruments were observing at the same time. Now, Pandora is one of these shepherd objects, and you can see it's accumulating ring particles. Here's an imaging observation. Here's our own instrument. Now, this looks pretty. It only has about 1/10 or 1% of the spatial resolution of the imaging camera. We have 356 spectral observations, 356 wavelengths, and here are some of them. Okay, and Pan. It's another object in the Encke gap. Here's a VIMS image. This is again, it has this skirt of material that was accumulated with time. There is a core body here with ring particles that it just accreted. And by the way, Pan was discovered by Mark Showalter on Voyager images that were obtained 10 years before he discovered them. Okay, so it's important to archive your data and have it for future generations. So here's the VIMS image, and here's just some of the other wavelengths we got. And here's Atlas, which is another shepherd. You can see that is really. It has it's almost like we called it the tutu, because it really has a big skirt around it of accumulated particles. We were able to get not only VIMS images, but here is a thermal. Sears was able to get a thermal map of it, because this is Carly Howitt and her team put that together. So I'm right there is where it would be visible. This is quite spectacular, and we're finishing up a paper for Science Magazine. If you do read Science Magazine, you'll see this in, I hope, a couple months. So I think I'm about at the end, nearing the end of my time. So I just want to talk about the questions. These are the major questions. What are the strange ridges and markings on these moons? We just don't know. The blue pearls, the walnut ridge on Iapetus, the red streaks on Tethys, we really don't know yet what made them. And this is a big question. I think Terry's going to be talking about this more on Enceladus and possibly the talk on Titan. Is there primitive life in the moon's subsurface oceans? Dione, as I mentioned, has a subsurface ocean. Enceladus definitely has. We're not totally sure about Dione. Is there primitive life there? Because all the conditions for life are there. How old are the moons and the rings? The moons are mainly ice. But what are some of the minor surface constituents? There's certain things that should have been abundant, like ammonia, that we didn't find there. We found in very small amounts, so we're still confused about that. And for further reading, go to our website. And I just published a book that you can get on Amazon, World's Fantastic, World's Familiar, Guided Tour of the Solar System. You can get that on Amazon or any other bookseller. But here's the website, saturn.jpl.nasa.gov, that has a whole bunch of information about this mission. I want to thank you for listening. Thank you.
Okay, so we're going to finish up with the last two speakers focusing on individual moons. Dr. Terry Hurford is a planetary scientist in the Planetary Geology and Geophysics and Geochemistry Lab at the NASA Goddard Space Flight Center. His research is focused on icy satellite geology and geophysics, the effects of interior structure on tidal deformation and surface stress, and the effects of orbital dynamics on tidal stresses, the influence of tidal stresses on the formation of tectonics on icy satellites, and the influence of tides in the eruptions of plumes on Enceladus, south polar regions. And that's what he will talk about now.
Thank you very much. Tonight, yes, I will be talking about Enceladus, this cryovolcanic ocean world, and really kind of how we interpret the Cassini data to kind of learn something about this surface and these eruptions that are coming from the south polar area. You've seen this image before, but I just want to give you the context for where we're looking in the Saturn system. We'll be looking at the small moon of Enceladus, which sits in the E-ring, as we mentioned before. And before Cassini, it wasn't clear that Enceladus was connected to the E-ring, but now I think you'll see through the talk that it really is the source of the particles that makes up this diffuse ring. Enceladus itself is a very small moon. It's only about 500 kilometers in diameter, 250 kilometers in radius. That's about the size of Arizona. If you've ever driven across Arizona, you've driven across basically the distance of Enceladus. So it's a very, very small moon. And it's got a small orbital eccentricity, and it orbits Saturn every 1.37 days. So because of its proximity, it has a very quick orbital period. The moon itself, from the pictures that we saw from Cassini, is very different in its textures. In the northern hemisphere, you have very heavily cratered terrain. And in planetary science, we don't really know the ages of the surfaces that we're looking at. But one thing we know is that if there's more craters, then it's probably likely older terrain. And in the southern South Polar region, you don't see very many craters at all. And the reason why you don't see them is that it's been resurfaced and covered over. There once were craters, but something has happened, some process has happened to erase them. And so that must mean that the terrain down here is much younger. So there's a dichotomy between the northern hemisphere, which is cratered, and the southern polar region, which has these fractures across them and very few craters. Cassini saw that it was an active body in 2005 and reported in 2006 through a series of observations with its instruments. These are two of the instruments that confirmed the presence of this activity. We've got the images from the ISS instrument that visibly saw the plumes erupting from the South Pole. In February and January, they saw these fuzzy light near the South Pole. These are images taken where the sun is actually on the other side of Enceladus, and the light is being reflected through the plume and then forward scattered into the camera. They were worried about scatter of light into the camera, so they took another image and rotated the camera with respect to the South Pole to make sure that it wasn't stray light that was causing their observation, and they could confirm that there actually was a plume. Another instrument, the Sears camera, which looks at the thermal emission of bodies, also determined that there was a hot spot near the South Polar region. And so the sun is shining near the equator, and you expect that the equator would be the warmest, near where the sun was shining would be the warmest region on the body. And so the fact that there was a large heat source near the South Pole also confirmed that there was something special going on here. And so all the data together kind of led them to understand that there's some activity going on at the South Polar region of Enceladus. So here's an image that shows you what geologically the South Pole looks like. This is looking right down at the South Pole, projected in the South Polar region. So the South Pole is in the middle, and you can see there are these 4 large fractures that run across the South Pole. We've dubbed them the tiger stripes. It looks like something that's just kind of took a swipe at Enceladus and dug in some fractures on the South Pole. They have names, Arabic city names of Alexandria, Baghdad, Cairo, and Damascus, and they're not in order. So Alexandria is the top one. You've got Baghdad, Cairo is kind of here, and then Damascus. But I'm going to zoom in on one region. So we got some higher resolution images, a few postage stamps of higher resolution images of these fractures. And so I'm going to zoom in on a fracture in this region just to kind of get you a feel for what it looks like at very high resolution. So this is one of the better Cassini images we have of the tiger stripe features. This image is at 12 meters per pixel resolution, and it's only about 20 kilometers across. And this is the Baghdad tiger stripe fracture here. You can see it's a trough on the surface, and you can see that there are boulders on either side of the flank of the trough. And this is an active region of the Baghdad tiger stripe. So I did a lot of studying of fractures on Europa, and one of the things that we learned from looking at Europa fractures, so these are actually images of ridges on Europa, is that a lot of times we think that the fractures form on these icy satellites due to tensile failure of the surfaces. And so on Europa, you can quite see there's a lot of ridges which formed along what we think were fractures in the ice shell. And some of these fractures have very distinct morphology that we call cycloids, and that they're these arcs of chain of arcs that we think form as a fracture it forms on the surface, and then as it propagates, the dynamical stress field causes the path of the fracture to curve. And so that creates this tiger stripe, or this cycloid feature. And so here's a model of that. We think that there are stresses on the surface, and they pull on the surface and cause a fracture. And the fracture then starts to propagate this across the surface, but the dynamical stress field is changing. And so as the crack propagates, the stress orientation changes, which causes the crack to curve and bend until the stresses get too low to continue propagation, in which it stops. And then the next day, when the stresses are high enough again, it starts the next arc on the cycloid. And so I just point this out. This is something we developed for Europa, but when we looked at the fractures on Enceladus, at least one of them looked very arcuate in nature, just like the cycloids. And so it kind of hints that maybe these tiger stripes have formed because of a dynamic response to tidal stresses. And so what does that mean? What can that tell us about these bodies? On Europa, we think the stresses are high enough to fracture the ice shell. These tidal stresses are high enough to fracture the ice shell because there's a liquid water ocean in the interior. And so if that's the case on Europa, then that might imply that there might be liquid under the surface of Enceladus too. And we can then model the stresses to see what it says about the formation of these tiger stripes. And so what are these stresses and how do they arise? Well, they arise because of the fact that Enceladus, and like Europa, is not in a completely circular orbit. So if Enceladus were in a circular orbit, it's tidally locked, so it has the same face pointing towards Saturn at all times. And if it were in a circular orbit, if you stood at 0 degrees longitude and 0 degrees latitude, you would see Saturn hanging above you in the sky, and it wouldn't move. But because the orbit is not circular, Saturn actually gets a little bit closer and farther from the surface of the moon during the orbit, and it also seems to rock back and forth in the sky, and that's what this picture depicts. And so at Perry-Center, you're a little bit closer to Saturn, and the gravity field of Saturn actually raises a tide on this small moon, Enceladus. And so if you're standing right at 0 degrees longitude and latitude, you'd be at the peak of the tide, and it would be pulling you a little bit closer to Saturn. And then as you move through the orbit, Saturn seems to recede a little bit away from you, and the tide that you're standing on would seem to fall. So just like when you go to the ocean and you see the tide rise and fall on the Earth's ocean, liquid water ocean, Enceladus is also deforming because of the tidal gravity field. Now, also because Saturn is rocking back and forth in the sky, the location of that tidal bulge seems to rock back and forth with respect to 0 degrees longitude. All of this is basically changing the shape of Enceladus throughout the orbit. And as you change the shape of the body, the surface is being stressed, and it causes stresses on the surface. And so this movie down here that I'm going to show you in a minute is the stress field in the south polar region of Enceladus. Here I've denoted the features, and I've denoted the stress field at different locations on the surface. And the blue lines are tension, and the red lines are compression on the stress field. And there's a little clock here on the side that shows you basically the position of Saturn relative to the surface, but not to scale. But as this movie plays, you'll see that the stresses are going to change. And then I've denoted the tiger stripe fractures. And if they're black, that means that the stresses are kind of pushing the cracks shut in compression. And when they turn to green, the stresses are aligned such that these cracks are actually in tension. Let me play that. So you can see right away the cracks change color. So right after pericenter passage, the stresses align. The stresses are moving in a clockwise rotational fashion, and they align such that they start to pull these cracks apart in tension. And then about a little bit after apocenter passage, the stresses are aligned to the opposite sense, and the fractures start to be pushed together in compression. This whole cycle repeats every 3.7 days. It's on the same orbital period as the body's orbital period. And so these cracks are experience a stress field that's changing very rapidly throughout about a one-day cycle. And so that we think that these stresses are also large enough to then cause the fractures themselves. So here's a quick model that we put together. So again, looking back at Europa, when we looked at the fractures on Europa, we noted that the stresses to form cracks on Europa seem to be in the range of 20 to 90 kilopascals. So these stresses can form the fractures on Europa, and if we look at what orientations are allowed for cracks on Enceladus, we can see whether or not they align with the tiger stripes. So at these different circles in the gray area, I've denoted the angles that are allowed by tidal stresses for a fracture to form at that location by stresses of 20 to 90 kilopascals. And then the blue lines show you the actual measurements of orientations of the crack around those locations. And you can see that for the most part, they agree fairly well with the gray allowed areas. So it seems like these tiger stripe features themselves, the orientation of them on the South Pole is very consistent with the orientation of the stress field that could form them. And again, as you saw in the movie, the stresses can rework these fractures on the surface, so they can kind of pull them apart in tension and push them together in compression on a daily cycle. And so in 2007, we predicted that if there are actually volcanoes coming out of these vents, then they should have some sort of periodicity to them, and that it should be easier to erupt while you're in tension, and maybe there'll be more eruption activity, and then less activity later on in the orbit. I'm going to show you some pictures of some pretty pictures then of the eruptions. Here's a nice image. Again, these are all done with the sun kind of on the far side of Enceladus, so high phase angles where you're kind of looking at light being forward scattered to the camera. You can see that you can't really see the fractures in the images, but you can kind of trace along where they would be on the surface. And you can see that right now the plume isn't actually uniform across the tiger stripe features. There are areas where the jets are collimated, and then there seems to be more tenuous kind of curtains in between them. And then not all the fracture seems to be active. Some places it's active, and other places it seems to be turned off, which is another indication that there might be some variability in what's going on the surface. Here's another image where you can trace the fracture into the kind of the dark terminator side of the planet. And you can really only tell where the fracture is by the fact that you can see the material illuminated once it gets high enough above the surface. But they're really stunning images, I think. And then finally, if you zoom way out, you can kind of see that this really is connected to the rest of the E-ring. We see something we call tendrils, where all this material is kind of then coalescing and forming the E-ring. And the fact that the E-ring itself isn't uniform in its appearance also tells us something about the variability in the output from Enceladus itself. So in 2013 and 14, about 6-7 years after we predicted the variability, VIMS and the Cassini data actually caught up and actually saw hints of variability in the plume output. So in this plot, we have orbital position. So 0 is at pericenter. This is apocenter back to pericenter. And then there's a proxy for the plume activity, which is the brightness of the plume from the VIMS and ISS data. And you can see after pericenter passage, there's a ramp up close to apocenter where the plume brightness intensifies, which is an indication that more material is being erupted from the vents. And then it ramps back down. And it repeats, these data are taken over many years, and so the cycle must come somewhat repeat every 1.37 days. We can kind of get a model for how this occurs. And so this red line is just a really simple model that says, if the fraction of the tiger stripes in tension are proportional to the output activity, then we can kind of model what is that activity. And we play a game of just looking at all the points on the surface of the tiger stripes, calculate the stresses on them at every point in the orbit, find out what fraction of them are in tension at any given time, and then relate that to the activity. In this model, we also had to put in the fact that the source is not at the surface. So even though the stresses might be in tension at the surface, if you go down a little bit into the subsurface, the weight of the ice shell kind of pushes the fracture back together. And so at some depth, the stresses actually have to be higher in order to break the vent open. But you can see that we can put together a pretty simple model that fits pretty well the activity that we see from the VIMS and the ISS data. Right. So what does this mean about the interior? So why are we playing these games on what's going on in the interior of Enceladus and the stresses? Well, we really don't know what the ice shell thickness of Enceladus is. We have some gravity data. Well, the very first ideas were that the ice shell was about 20 kilometers thick. And we've got some gravity data more recently that isn't very good at constraining just how thin the ice shell can be. It can be very thin, or it can be up to as much as 40 kilometers thick. So the data itself isn't very conclusive. We've also got some researchers have looked at how the body rotates and librates, and have concluded that the ice shell can be really thin and about 10 kilometers. But regardless, 10 to 40 kilometers, that's a lot of ice to break down. These fractures really can only penetrate 1 to 3 kilometers in depth from the tidal stresses. And so if we're really erupting material, water material, can we get to that material? That's the important part. If you think of these ice shells kind of like glaciers on the Earth, if you go out and you see a glacier in the ocean, you know that 90% of it is below the water line. And that's just kind of where water wants to go up to onto an ice shell. And so we think that if you have this ice shell in Enceladus, you should be able to percolate water up at least 90% of the way to the surface just by the difference in density between the water and the ice shell itself. And so with a 10 to 40 kilometer thick ice shell, that means you should be able to get water up, infiltrating somehow into the ice shell up to a level that's just 1 to 4 kilometers below the surface. And then these fractures, like I say, can penetrate down 1 to 3 kilometers. So it seems like it's plausible that the cracks can then reach this water table and then erupt the material that you see in the images. And in fact, we have some evidence that these plumes are linked to the oceans, and it's really important for the habitability of Enceladus. So the Cassini spacecraft has actually flown through these plumes, and with different instruments, has actually taken samples of that material and analyzed it to figure out what's in the plume. We know that there's water particles and there's some salt particles, but the Cassini instruments also found these silica nanoparticles. And these are really important because these are formed on Earth in hydrothermal vents where hot rock is in contact with liquid water. And so if the ice shell doesn't have rock in it, it must mean that there must be vents of hot material down at the bottom of the ocean where we think there's a rocky core in Enceladus. And that material, that hydrothermal vent area on Earth, we know that that's a great place for life to form that's independent of photosynthesis. You have this hot material that's coming out of the Earth, and you have colonies of microorganisms at these black smokers that can live just fine at the bottom of the ocean floor. And so we think that maybe, possibly, there could be something analogous going on Enceladus. We know that there's these hydrothermal vents. And then we've also detected molecular hydrogen in the plume too. So we think that there are the right conditions for life in the oceans of Enceladus. And we think that material is getting up through the ice shell and is being sprayed out into space. And so it's something that it's a great place to go and then look to see whether or not life does exist. So just because the conditions for life exist doesn't mean life itself exists in the ocean. And so I think in the coming missions back to the Saturnian system, one of the high priorities will be to fly through this plume material with the instrument and then actually look for these prebiotic life signatures. So in conclusion, Enceladus, I think, is the biggest little moon in the solar system. I mean, it's a really small body that's very interesting. It has an ocean in its interior, and that ocean is able the ice shell is able to dissipate enough energy to keep that ocean liquid, and then the tidal stresses are able to fracture the surface and allow that material to vent into space. And that ocean, we found, has got the conditions to support life. So really, it's up to the future missions to go back and look for life in those plumes. Thank you.
Okay, so last but not least, we come to Titan and Dr. Conor Nixon, who is a planetary scientist at NASA's Goddard Space Flight Center and the deputy principal investigator on Cassini's composite infrared spectrometer, known as CEERS, which he also helped to design, build, and test, will be the next speaker. Conor began working on CEERS as a graduate student at the University of Oxford in 1995 and joined NASA in 2000 to continue this work. He was named co-investigator for CEERS in 2007, and then the CEERS Deputy Principal Investigator in 2012. Thank you.
Thank you very much. Okay, well, following those amazing talks, I'm going to round out our tour of the Saturn system by talking about Titan. So Titan is the largest moon of Saturn. It's actually the second largest moon in the solar system. It's one of the most fascinating objects in the solar system. So it's really the closest thing there is as a moon that could be a planet, that has all the features that we would otherwise think of as a planet, right? With an atmosphere and so on. So you can see here some clues as to what I'm going to talk about on Titan's surface. So actually, one of the things I'm going to focus on, because there's so much we now know about Titan compared to what we knew before Cassini, is I'm going to focus a lot on Titan's atmosphere and the chemistry, which to me is the most exciting part of Titan. I'm going to talk a little bit about the surface, but there's a whole other world of geology down there, which is a whole other talk. So, as I said, I'm going to talk about the chemistry of Titan's atmosphere, some of the different environments on Titan on its surface, and then how these things can relate together. And what is the potential of Titan for what we call astrobiology? So astrobiology is the field of searching for life in the solar system and beyond, in fact, amongst the stars. Okay, so starting with Titan's atmospheric chemistry. So I always like to start my Titan talks with this slide, which just shows that Titan is different. You can see right up that Titan is featureless, really, when you look at it. And the image here of Titan in the top row is from the Voyager encounter of 1980, and most of the other moons in the solar system, you look at them and you see craters, you see cracks, you see fractures. You can see the surface because there's nothing there. It's like looking at the Earth's moon. But when you look at Titan, you don't see that. It's like looking at Venus. So you know right away that you're looking at an atmosphere. And it's a dense atmosphere as well because you can't see through it. And in fact, this originally led some of the early scientists to believe that Titan was the largest moon in the solar system, and that's because what you see is actually the top of the atmosphere, and that adds a couple of 100 kilometers to the apparent size of Titan. So it's like looking at someone when they're wearing a snowsuit, right? And they look bigger than they would be without the snowsuit on. So Titan's got this kind of giant sheath around it, which is the atmosphere. You know, and that really makes Titan so much more different and in some ways really interesting in the solar system. So you can see here a close-up of the edge of Titan, what we call the limb of the atmosphere. From Voyager 1, you can see right away that there's kind of this main orange haze, which we now know is an organic smog. And this is similar to some of the things you can actually get on the Earth, even in the LA basin. If anyone's ever been to LA on a smoggy day, and I did this recently, you drive up out of the city, and then you look down, and all of a sudden, you just see this kind of orange haze. So that's like Titan's making its own haze. And then above the main haze, you can see there's these other layers kind of floating serenely above the main haze. And there's all kind of chemistry and dynamics which are causing these phenomena to occur. So Voyager carried a bunch of instruments on it, and as well as the cameras, it carried a spectrometer, which we heard about earlier. A spectrometer is just an instrument which splits up light into its different colors, or what we look at here is looking at heat. So we're really looking at different colors of heat. And when we look at Titan, all of a sudden, something that looked very uninteresting, and just this orange blandness turns into this very, very rich chemical complexity. So you can see here, there's all these peaks. Let me see if I got this. Oh, wrong one. Let's see. Okay, let's go back. There we go. Okay. You can see all these peaks, which are actually different molecules. So each molecule vibrates in a different way, and it vibrates at a unique frequency. It's like tuning your radio dial to different frequencies, and you tune into these different molecules. So each one has its own infrared fingerprint, and you can actually look at these peaks, and then we can line them up with work we do in the laboratory on the Earth and say, okay, this one is methane, this one is ethane, and kind of tune into these and decode this entire fingerprint. So you see there's a lot of rich chemistry going on in Titan's atmosphere here. One of the things we now know is the atmosphere is mostly composed of two gases, and that's nitrogen, which of course is the main air in this room that we're breathing, 78% nitrogen on the Earth. Titan's about 98% nitrogen. But then instead of having like oxygen that we have on the Earth being the second most abundant gas, on Titan it has something else instead, which is methane. And those two things can actually react together and cause all this rich chemical complexity that you see here. So after Voyager, as Julie said right back in the first talk tonight, we wanted to go back. We saw that there was so much going on there, but Voyager was just a flyby. We wanted to go back, wanted to orbit Saturn and look at these moons. And as you heard, there were 127 flybys of Titan. So Titan was not only just a convenient gravitational boost, but of course, there was all the science that we did every time we flew by Titan. So we built the Cassini spacecraft. Cassini, you see here before launch, it's about the size of one of those kind of small school buses, not like the really long ones, but the kind of shorter school buses. You can see on the side here, this dome on the side, this is the Huygens probe, which was taken specifically to land on Titan's surface. That was built by the European Space Agency. So once Cassini arrived, it got to Titan and started doing its first few flybys. We began to immediately see even more than we'd seen with Voyager. And one of the instruments that we had on board was an ion and neutral mass spectrometer. So if any of you are chemists or biologists in the room, you might have come across one of these machines. It takes atoms or molecules, turns them into ions, and then it deflects them in different ways. And by measuring the mass, you can get this pattern. What this is telling us is that these are all carbon-based molecules because we have these repeating peaks about every 12 to 13 mass units, which tells us that we've just added another carbon atom to a chain of carbon atoms, and it's like adding Lego bricks. So we've added another carbon atom, we've made another series of molecules. And in fact, this is when we realized that we didn't build Cassini's instruments in some senses sophisticated enough, because this instrument only went out to 100 atomic mass units. And in fact, we can see here that the pattern showed no signs of ending, and we could have easily gone beyond that. In fact, another instrument on Cassini was able to go to higher masses and look at even bigger, heavier molecules, and this was the CAPS instrument. And you can see here the CAPS spectrum. It doesn't have quite the same resolution, but right over on the top left here, you can see those spiky peaks, and those are the ones you just looked at right here on the previous figure. You can see these 6 or 7 big peaks, and these are the ones that are right over on the left here. And then the spectrum continues. The mass spectrum shows there's even more molecules at all masses, even heavier and heavier and heavier masses. And here on the right, you can see that the negative ion spectrum is going out to tens of thousands of mass units. So now we're getting beyond just a molecule. We're getting up to like a soot particle, a grain. Now, of course, we don't know the structure of all those because our instruments could only give us a glimpse as to what the structure was. But by doing experiments in the lab, we can try to simulate some of the things that are going on in Titan's atmosphere. So we can literally get like a glass jar, a glass vessel in the laboratory, put in some methane and put in some other gases, nitrogen if we want, pass a spark through it, make a discharge, and then start to cause chemical reactions. In fact, I noticed out here in the foyer of the Cosmos Club, one of the pictures hanging on the wall is famous scientist Harold C. Urey, and he was one of the first people back in, I believe, about 1958, who did this experiment Miller-Urey experiment that made these complex molecules from more simple gases. In fact, Titan is doing this experiment for us right now. So if we do this experiment in the lab, and we just do it with carbon and some benzene rings, we can begin to build up things like this. So a benzene ring is a hexagonal ring of 6 carbon atoms. And experiments done by Dolitsky and McKay showed that there's 2 different ways we could join these rings together. We can either fuse them together, so they're really kind of joined onto each other, holding hands, or they can have this more tenuous hydrogen bond between them. And they showed that these are some of the examples of things that are going on in Titan's atmosphere that are some of the things in that mass spectrum that I just showed you. So here's a nice graphic that just summarizes some of our knowledge now. We're beginning right at the top of the atmosphere. You can see with the methane and the nitrogen, it's being reacted primarily by 2 things, which are UV sunlight, the same thing that causes you, to get sunburned on a clear, sunny day, but also charged particles from Saturn's magnetic field. The electrons are like in a big particle accelerator going around in Saturn's magnetic field, and these all impact on the Titan's atmosphere, and then they react and cause heavier and heavier molecules to be formed, and then this causes this orange smog that we see. So we think that we've learned a lot about that. So earlier on I showed you the Voyager Iris instrument. I showed you these molecular signatures, these fingerprints of different molecules. When we went back with Cassini with an instrument that was about 10 times the separation sensitivity of the Iris instrument, this is what we saw. So now we can see even more finer gradations of molecules. In fact, we were able to detect 1 or 2 new things that hadn't been seen by Voyager. And of course, we can measure all these in much more detail. And because Cassini made 127 flybys, whereas the Voyagers only made 1 flyby each, we're able to go back time and time again and look at how these molecule signatures changed over time in accordance with the sunlight that was reaching the atmosphere. So Cassini told us a lot about Titan, and in fact we were able to bring in some of the ground-based observations that you've heard about using telescopes from the ground. And one of the instruments that I've been active with in recent years is actually this instrument here. This is in Chile. This is in the Atacama Desert of Chile at 5,000 meters. So this is way, way high up in the Atacama Desert. And these telescopes are able to be above most of the water vapor in the Earth's atmosphere. And they can actually look out. And of course, we use this telescope to look at Saturn and Titan while the mission was unfolding to try and give us more information. And we detected some of these other molecules, which we suspected were seen by Cassini as well, including this one, the ethyl cyanide and vinyl cyanide. You can see these peaks here. So a similar thing to what Cassini was doing, but now doing it from the ground and looking at the fingerprints of these molecules in the radio waves at longer wavelengths. So these are all the things that we know right now to be in Titan's atmosphere. These are the ones that have been definitively identified by their fingerprint. Of course, we would love to go back and actually do a deeper flyby through the atmosphere and see if we could identify more of the ones that we see in the laboratory and line them up with what we see in Titan for certain. And there's several chemical families that we see here. We see the carbon molecules with the rings and the chains. These are the dark gray atoms you see here. And then when we begin to add hydrogen, which is the cyan, nitrogen, which is the blue, and then oxygen, which is the red, you can see that we're developing these different chemical families. So now the question naturally arises, how complex does this chemistry go? Is this something that could be like the atmosphere of the Earth in the very early days, maybe 4 billion years ago when the Earth's atmosphere was forming, and actually forming these molecules that may have been the precursors of some of the molecules that we know are needed for life? So if we look at something like a DNA molecule, we see these carbon rings again in the structures of the nucleobases. So Titan is it's getting there, and the thing that I'm most interested in is trying to bridge that gap. Where does Titan go to, and where's the simplest building blocks of life, and how complex things can arise on Titan? Okay. So let's look a little bit at Titan's surface. So we know there's all this going on in the atmosphere. We have these molecules, they're reacting. They go through Titan's atmosphere, which is like a giant chemical plant. It's just making all these reactions, making all these molecules, churning them out, and now they're coming down. Where do they go to? Well, in fact, with Cassini, with its radar instrument, it was able to look at the surface and see that there's actually lakes on the surface. these are lakes of hydrocarbons. So really, you can think of it as like lakes of petroleum products that are just, this is Titan's North Pole, and it has these lakes, and these are actually a comparable size to the Great Lakes of North America. So if you think Lake Superior and Huron, Erie, these are the similar size, and these are giant hydrocarbon reservoirs that I'm sure some of our energy companies would be interested in if they were a little bit closer to hand, maybe, but a little bit far right now. But these are methane lakes, and in fact, there's been proposals to go back to Titan in the future someday, and maybe even land a boat and float a boat with some scientific instruments on some of these hydrocarbon lakes. So we know that this stuff is being made in the atmosphere. It's coming down every day. It's raining out on the surface. So Titan literally has rainfall, but not rainfall as we know on the Earth. In fact, it's rainfall of liquid methane. So it's very cold on Titan. So here's a kind of schematic of what's going on. Some of the methane and the other products are coming down. And when they get to the cold lower part of the atmosphere, they're raining down, forming lakes and seas on the surface. And then some of this is actually re-evaporating, and we can see clouds of methane that form on Titan and cause storms to happen. And of course, the other interesting question is what chemistry is going on now in these lakes. And because Titan's surface is mostly water ice, now we can add in another ingredient, which is a lot of water ice, which is not in the atmosphere. The atmosphere is too cold for water ice. But one of the things that Miller and Urey showed is that when you hydrolyze complex organic molecules and add hydrolysis, add the OH group, you can start to get some very interesting amino acids forming. So this is the map that we have at the end of Cassini. It's a map that we didn't have anything like this from Voyager. In fact, Voyager was never even able to see the surface. Cassini's told us a lot. We can see here in these equatorial regions, there's these vast dark plains where we believe it's organic material that's kind of dried up, and it's forming dune fields, similar to like the dune fields you would see if you went to maybe the Kalahari Desert in Africa. But these dunes are not silicate material. These are actually organic particles. So just think like little chips of plastic that are blowing around in the wind, and they're forming big streaky dunes. They're wrapping around some of these icy cratered terrains. And then right up in the north, in the upper left here, you can see the lakes, which are just stretched out because of the perspective. And even though this is a great enhancement of what we had before, of course, we'd love to go back and get a much more detailed view of Titan. But because of the cloud layers, we can't just go back, put a spacecraft in orbit with some cameras. You just cannot see through the surface. We would need something like a radar, again, to give us more complex mapping. So again, another close-up of these lakes and some facts and figures about the sizes and amounts in the lakes. Okay, and again, just showing the Titan, you can see that the dotted line here is the temperature profile of Titan, so showing that it gets very cold, down to about 80 Kelvin in the lower atmosphere. So that's about, was it minus 190 Celsius. So very, very cold, cold enough to condense methane and form these clouds and rainfall. So I'm just going to finish up by talking a little bit more about the astrobiology. This is the thing that really interests me, is what's the potential for life on Titan. So first of all, we can think about the Earth. The Earth is the only example of life that we know about. And what things do we need? We need a solvent, so we need water. We believe that all life on Earth requires water. Then we need a compartmentalization. We need a membrane. We need something to hold in the guts of the organism to contain all the DNA, so that it's not just distributed back out into the fluid. And we need something to encode information. That's our DNA, of course. And then we need structural molecules. So these would be like the proteins. And we can think, what would those things look like on Titan, where we don't have any liquid water, but we have a liquid methane environment? So I talked earlier a little bit about the chemistry that goes on, possibly on the surface, when these organic molecules and they meet the water, the frozen water of Titan's surface, and that's adding the water, the H2O. So you see here these arrows indicating that we start with the molecules that we see in the atmosphere, then on the surface we can add the water to it, and then maybe get these other types of oxygen-containing aldehydes and ketones. So one of the most interesting things, and the reason why I brought in the ALMA results from the radio telescope on the Earth, is that the ALMA telescope was able to confirm one of the molecules that we suspected from Cassini, and that's this molecule you see here, vinyl cyanide. In fact, if you go and Google this, you'll find all kinds of NASA press releases about it. And the reason is because prior to our discovery of this, I was a member of this team, was that another team up in Cornell University, where Phil is from, had predicted that the vinyl cyanide molecule, if you put it in methane liquid, it would just form into a spherical membrane. And this could be the key to creating life, because you need to create your membrane first. And it turns out the vinyl cyanide molecule is one that can just kind of link up kind of head to toe with itself and maybe form into this structure. So now this could be the key to forming a membrane. And then just like a year later, we confirmed for sure this molecule is actually on Titan. So that was really exciting. It was really exciting for NASA and really exciting for people studying Titan. Another thing that was proposed was that the HCN molecule, it's a simple hydrogen cyanide molecule, can actually twist into a spiral, and this may be a spiral this would not be a DNA spiral, but it'd be something that would form sites for catalytic reactions that could allow other more complex reactions to occur. So here's our summary of where we are with Titan astrobiology. We have a solvent. The solvent is the liquid methane. We think we have the compartments that we need to form the membranes. And we have structural molecules, which could be these carbon sheets. What about information storage? So that's the thing that maybe right now we need to think some more about. How could we encode something that would be similar to DNA on the Earth, but in a very different chemical environment? So recently we've started a new initiative. It was just confirmed a couple of months ago that now we have a 5-year team together. I'm working together with JPL and some other teams to really look at Titan astrobiology in detail. And these are some of the things we're going to look at. We're going to look at the molecules falling out of the atmosphere, how they react on the surface, and maybe even deep inside Titan, where there could actually be real liquid water deep inside Titan, and that could do very, very different things. And we could get things similar to we've seen on Europa or Europa and Enceladus. Okay, so these are just a summary again of some of the processes that are needed to build life, and we can see here on the right-hand side things that are known to occur on Titan, things that we believe to occur on Titan, and things that now we're getting to the limits of our knowledge. So this gives us kind of a roadmap as to where we need to go to. So in summary, Titan holds a strong potential for life, but maybe not life as we know it. It's the only place in the solar system capable of supporting life in a non-aqueous environment, maybe. But also Titan has water too. So sometimes when we talk about, NASA now has an initiative called Ocean Worlds, which is the study of Europa and Enceladus and all these moons that have the liquid water inside them. And Titan is like a 2-ocean world. You get 2 for the price of 1. So you get methane on the surface, but then deep inside, there's actually a liquid water ocean as well. And this has given rise to some really interesting ideas for future missions, which I mentioned could include having a boat or a floating capsule, shall we say, on the methane lakes, maybe an airplane. Of course, Titan's got an atmosphere. You can't do this on the moon. You can't do this at Europa, but you could do this on Titan. You could fly an airplane. It's got a thick atmosphere. Submarine, right? You could have something that would go below the surface of the lakes. In fact, one of the most exciting ideas of all has recently been selected for further study for an actual flight mission, and that's this mission, which is called the Dragonfly, and this is actually a quadcopter, which would be like a giant landing craft on Titan, but kind of similar to the rovers that we have on Mars. But instead of having wheels, we would actually use Titan's low gravity and its dense atmosphere to just lift off using a quadcopter and just relocate this landing craft and maybe land a few miles away. And this could go on for a long time. This is powered by a very small nuclear energy source, and this could land and take different experiments in different parts of Titan. So I'm going to stop right there, and thank you all very much again for your attention.
Okay, we're going to have a question and answer session now, so we're just bringing up the chairs. I wanted to take a second, in addition to thanking the speakers once again, to also thank other members of the Cassini team, some of whom are here tonight. So one more round of applause for the speakers and for other members of the Cassini team. So if we can just have the speakers come up and take a seat, and as soon as everybody's comfortable, we'll take questions. Okay, first question.
Hi, Joel. I'm a member of the Society. Really enjoyed all the presentations. Had two questions. One is on the moons that you thought had ring structures but that had collapsed. Do you have any modeling for how the collapse would occur? Would it be because of maybe some radical shift in the moon's mass may have caused a gravitational shift and it might have spiraled in? And the second one is more for the engineering on the spacecraft. Is it not correct that Huygens had microphones on it, and when it came down, you turn on the microphones and you heard some of the wind going across the surface of Titan?
Okay, so yeah, you're essentially correct that the moon's planetary moons are made up of small particles. And okay, maybe I'm not on. Do people hear me now? Okay, so planetary moons are made up of small particles, and they collide and lose energy, and eventually they just collapse onto the planet, or in this case, moon. After a while.
I actually don't remember the microphonics.
There were some.
There was a descent imaging radar, and there was a spotlight at the end. But I don't remember microphones.
There were some radio receivers that picked up electrical disturbances. I'm not sure if there was actually a microphone. There were electrical impulses detected by Huygens that there was a lot of argument about in the early days exactly whether these were lightning flashes, some were occurring somewhere on Titan. And I think in the end they were thought to be something called a Schumann resonance, which has to do with a reflection between the ionosphere and the surface. You get them on the Earth. I don't think there was an actual physical microphone.
Yeah, I don't.
Was there?
Does anybody want to check Wikipedia?
Google can tell you anything.
I'm Bob Hershey. I'm a member. What are the plans for following some of the things we've seen tonight and seeing if there are undiscovered things like maybe better signs of life?
So I think right at the end there, you saw I showed a couple of the mission proposals. The Dragonfly mission, the one right at the end, is one of the ones that's actually been selected for what we call Phase A study, which is a one-year study, and it's up in competition against a totally different mission, which is a comet sample return mission. But some of us who are Titan fans would love to see that one go ahead. But there's also been proposals for missions to Enceladus to go back and kind of go back and have a more detailed look at the plumes and actually look at the composition of the plumes in more detail. And maybe someday far in the future to land on Enceladus. But right now, Enceladus is giving us a gift, which is these plumes, which makes it a little bit, almost unnecessary to go land on the surface because we can see right inside from what's coming out. So also there was a Saturn entry probe which was proposed. So on the Galileo mission, Galileo carried a probe which actually went into Jupiter. But on Cassini, we did something different. Instead of taking a probe that was going to go into the central planet, we had the probe which went on the moon. That was Huygens. So we didn't have a Saturn probe. And there's been a proposal called Sprite, which would be a probe that would actually go into Saturn's atmosphere and tell us more about the in-depth composition of Saturn.
Something that's slightly different there too is there's of course a Europa mission, the next big flagship that NASA is planning is a mission to go back to Europa, which is an icy moon of Jupiter. But there have been Hubble observations, a bit controversial, but they seem to have been confirmed, that show there may be some kind of plume activity on Europa. It's not nearly as clear as the Enceladus ones, but so it might be that the first time we get to go back and look closely at plumes might be Europa plumes with the Europa mission.
Tim?
Timothy Thomas, I'm a member. If the Cassini team had wished, did they have the power to change the rings of Saturn in some permanent way, such as striking one of the shepherd moons or orbiting in or very near the rings? If that was your intention, could you do it?
Well, yes, we could have hit the rings. We could have hit a lot of things. We were directed by NASA, by planetary protection, to specifically not hit Titan and not hit Europa. We had talked about, whether we would hit the rings or not. I don't know that we would change the composition. We actually weren't that big in terms of overall mass. But, and we didn't know for sure. I mean, we hit this area that turned out to be the big empty in those last 22 orbits, but we weren't sure that we weren't going to hit the D ring on the way in. We hoped that we didn't, but there was no specific. One of the things that you had is, in this day of instant wireless and instant communications, the picture that Phil showed at the end, we didn't have the ability to send back pictures on the way in. We only had the ability to send down low kilobits of data. So we were actually only sending down the ion and neutral mass spectrometer data and the magnetometer and some of the low field instruments. So you wouldn't have been able to really do a picture and really have a splash. But no, we weren't, we wouldn't have been able to do anything like that.
Worth keeping in mind that although I pointed out that the rings are physically very thin, only maybe 10 meters, but they have an awfully big surface area. In fact, the rings in diameter, a nice way to think about them is that they're almost a light second in diameter. It takes almost a second for light to get from one side to the other. So if you add up all the mass in the rings, it's about a half the mass of the satellite Mimas, which was one that Bonnie didn't show, but that's a little smaller than Enceladus. So maybe the rings altogether are a quarter or something of the mass of Enceladus. So there's a lot of stuff there altogether. So unfortunately, I think Cassini would have disappeared without a trace. If it dropped it into the rings, it would have been destroyed, but it would not have produced any. Maybe there'd be some plutonium left back and pick up. That's a good point.
No.
There's not much plutonium naturally in the rings, so that might have survived.
Carl Merrill, I'm a member. You showed the pictures of this probe being parachuted onto the surface of Titan, I think, but I didn't hear any data, or what did it do after it landed?
Oh, I'm sorry. It transmitted, that was one of the frequencies. So the idea was the probe was ballistic, dropped up on its own accord, but it transmitted its data as it was descending, and this descent imaging radar. I was thinking Conor might talk Titan, so I didn't put pictures in there. But there is a picture of Titan at the after Huygens landed, and it lasted for several hours afterwards. We only tracked it for a few minutes, but it radiated its data back to Cassini, and we stored it on and then turned around and played it back to Earth. And the thing that Bonnie said about, they had this great chance of Iapetus on January 1st, but we were holding real steady to be able to go back and get the probe data. So it radiated the data back.
So what was the data?
Well, there was the descent imaging radar, so they took pictures all the way in. There was a surface analyzer, and that crunched into the surface. There were 6 instruments on Huygens. I used to have them written down.
I can comment a little bit as
Okay.
well. If I had more time, I would have gone in more depth into the Huygens probe, but it was really complementary to Cassini because it actually went into the atmosphere, whereas Cassini just kind of went through the outer fringes of the atmosphere to stay safe. But the probe went down. It was actually able to do some of the things like measuring the isotopic ratio of deuterium to hydrogen and carbon-12, carbon-13, things like that that are fundamental to our understanding of how the planet or the moon formed from the solar system. But also one of the really cool things was that just about 10 or 20 kilometers above the surface, when it kind of broke through the haze, it was able to finally take really close-up pictures, and it showed these river networks. So there's these dried-up river channels that were carved into the icy surface. And where Huygens landed, we think it was like a dried-up seabed. So maybe in Titan's past, it actually had much bigger oceans of methane than these lakes that we see today. But many of them have vanished over time, so maybe the methane's kind of get used up over time. But you can see these river channels where clearly there's been a lot more heavier rainfall in the past, and it's carved rivers into the surface. That was one of the greatest things from Huygens, I think.
Yeah, and the surface, so when it did land and the images it sent back from the surface showed rocks that had been rounded from flow in these river channels.
Cobbles, yeah.
I took those pictures out. They were science. Sorry.
I don't believe you said that.
Pardon?
There's also a recording of the sound, or whatever it was, as Huygens went down to the surface. I think it's on the internet. Blue microphone?
Yes, my name is Mike Hilton. I'm a retired aerospace engineer. And almost 40 years ago, I was working at NASA headquarters in 1979 as a advanced studies manager for planetary missions. My boss came into my office one day and he said, "Mike, we have a new mission to work on. It's called the Saturn Orbiter Dual Probe." And so he talked a little bit to me about how it works and what it all involves. And he says, "Why don't you draw up a sketch on that, take it to the art department, and we'll use that in a presentation to try to get the mission approved." So I did that, and it wasn't that sketch that necessarily got the mission approved, but it was added into everything else. And I happen to have that pencil drawing that I made at that time and the artwork that was done that showed the mission and all the details of how it worked. And in this case, it showed a probe coming off the spacecraft as it approached Saturn to go down to Saturn. But then in the intervening years, of course, the budget was cut and that probe was cut out. However, the Cassini probe itself was the second probe, right, to go down to Saturn. So it was a dual probe mission. But I'll let you take a look at these if you like.
Oh, wow. Yeah. It's telling us something we didn't know.
If you have a question, raise your hand so the person with the mic can get the mic to you.
Hi, I have a question about the process of talking to the spacecraft.
Oh, yeah. Could you stand up and tell us your name and whether you're a member?
I'm Colin Cannell. I'm not a member. I'm just a random tourist. So if you're an engineer and you want to tell the spacecraft to do a burn or change its position or send back certain data, or if you're a scientist and you want to tell an instrument to do a particular measurement, I presume you come up with what you want the spacecraft to do, and then at some point someone has to actually transmit that. How close are you to the actual transmission? Do you know the language that the spacecraft speaks, or is there a team that's going to translate your intent into a series of commands, or how does that work?
It's called the sequencer, and we actually sent up a series of commands that we actually sequenced the spacecraft for up to 10 weeks at a time. Towards the end, we would go 5 weeks, but usually we would send up sequences, and they're pretty simple. It doesn't take a whole lot of work, but back in the late 60s, JPL developed this SeqGen, sequence generation, and sequence translation, SeqTran. And so we took the actual commands in a human readable form and then translated them into Ada code and then translated them into ones and zeros. And the sequences were then stored on board by the onboard computer and then just clocked out, a command at a time. So we would send up, like the burns, when we would do a maneuver, we would send those up close to real time's a hard thing because I told you, it takes an hour and a half for the data to get there. So we would send it up maybe close to 3 hours, 4 hours before a burn would happen. But we would put the sequences up 10 to 12 weeks at a time. We would send those up to 3 weeks at a time. You had to wait till the path sequence clocked out enough to leave enough memory. I think there was only 150K words of memory that created the sequence. These are pretty simple commands. It's not complex language.
I might also add that before we get to that stage, scientists get together and plan each sequence. We decide which instruments are going to be on, and usually they're all on, but one is leading the observation. We check the data volume, the power, And then these kind of conceptual observations are translated to instrument commands. And those are usually pretty simple computer language, and they're all triggered by a clock that's on board the spacecraft. So all these series of commands are put together. They're tested by spacecraft model for data volume, power, and everything. And then they're uploaded to the spacecraft, as Julie said.
And once we got closer, if we were not exactly where we thought we were, so if we were pointed at one of Bonnie's moons and we were not exactly pointed because we were a little bit deviated from the trajectory, we could send up an overlay and then say, instead of pointing at you, now the spacecraft is in time pointing over here, but I really want to point at you, so I'll correct and point over here. And that's how you got those incredibly just detailed bulletproof pictures, where the spacecraft was capable on reaction wheels of holding steady for microradians pointing, and that's why those pictures are so good.
I think we'll have three more. We have the green microphone here, the blue microphone there, and I think Carrie had a question in the back, so he gets the red one. And if you don't have one, make one up.
John Wetmore, I'm not a member. There's no mention here made of Pioneer 11, and I was wondering if the data from that early mission was still of much use when you were busy planning Cassini.
I won't say it wasn't. There's a lot made about the Pioneer 11 anomaly and the time and things like that. We used a lot of navigation data because basically we tracked the spacecraft and all of the satellites by Doppler, the change in frequency. So Pioneer 11 was still active and the Voyager data, but in terms of planning Cassini, not really. Is that a bad answer?
Well, I think Pioneer was a bit unfortunate in the sense that it flew by Saturn in 1979, I think. So it was only a year before the Voyagers. So while it was the first mission to Saturn, the Voyagers were much more capable spacecraft in terms of the scientific instrumentation. So they basically supplanted the picture of Pioneer 11 in the minds of the public and most of the scientists. But Pioneer 11 had a lot of unique charged particles and fields instruments on it. It was more that kind of spacecraft. So I think it did a better job of mapping magnetic field first and then some of the radiation belts. So it gave us some concrete knowledge on that. And I remember even with the Voyager flybys, the actual distance, how close we came to the rings and some of the moons, was we were able to plan that with more confidence because of Pioneer 11 had gone through some of those same regions and said, okay, this looks like it could be dangerous, but in fact we flew through there and it was okay.
Yeah, Phil just mentioned exactly what I was thinking after I said that. We knew where Pioneer 11 flew and where the two Voyagers flew. And so when we did the Saturn orbit insertion, we were going right into where the Pioneer and the Voyagers went so that we could do our burn to slow ourselves down for Saturn. And we knew we weren't going to probably hit any ring particles on the way through there.
Hello, my name is Derek. I'm like Colin. I'm just a random fan engineer. Saw a Facebook post, came out. I actually had numerous questions, but I won't even get into it in fear of someone being too rudimentary. But largely where I was really interested in is the life of the actual Cassini and some of the redundancies that was built into it and whether that came into play into how you were able to just extend it out way past the original mission. And knowing, it seemed like there was a little bit of luck involved, like Titan's ability to give you the gravitational. So is it like, what kind of things did you guys put in there just in case you were hoping it would get extended in the life of it, or?
Well, you put everything on the spacecraft just hoping you get there and you get the 4 years. The extension was just because we had a healthy spacecraft. But for example, we needed 3 reaction wheels to point the spacecraft very stable. We carried 4. We carried one that could turn in the direction of any one of the 3. And actually, before we even got to Saturn, we'd had to use the redundant wheel because one of the primary wheels was very noisy and cranky. It sounded like You ever lost an axle bearing on your car and the rear axle? It was kind of like the rear axle when bearing was on the highway. So we took that one off. We replaced the thrusters. There's a series of 8 little quarter-pound or 1 Newton thrusters. That's how quarter-pound. Think about a quarter-pound of thrust. And we had to go to the backup thrusters in 2009 because we started having problems with a couple of the thrusters. We lost the ultra-stable oscillator in 2011, and we redesigned the way we did the radio two-way Doppler series. So the thing that I have learned over 30 years of working on spacecraft is if you have the capability, it will be used. We also crashed into Saturn with a completely good plumbing system in the biprop. We were out of propellant, but the gas tank was empty, but the fuel lines all worked. We carried 2 radios, 2 IRUs. Everything else was redundant.
So one thing Julie was a bit modest about, she mentioned that we were out of fuel at the end. I mean, the fuel tanks the gauges had been on empty for months before we actually dived in. We just didn't know how good they were. But most of the fuel, as Julie said in her talk, was used en route to Saturn, and then the big burns to get into orbit around Saturn and correct it. So at that point, we'd used
most of it.
I was going to say 90%, maybe not, maybe it was 75%. But most of the fuel had been used for the main engines. And the rest was expected would be needed to clean up. Whenever we flew by Titan, it wouldn't be perfect. So you track the spacecraft afterwards and say, okay, we're a few centimeters per second faster than we intended to be. We need to fire the engines to eliminate that erroneous velocity, or it'll grow and the spacecraft trajectory will divert. The engineering team got amazingly good at this. And while they originally budgeted a certain amount of fuel for every flyby, and they said, well, maybe we can do 40 Titan flybys, but that'll use up the whole budget probably. By the time we got to 40, they were using so little for each flyby that they were becoming almost free. They were saying, well, maybe another 100 isn't out of the question. And by the end, they were nailing the flybys so well that the spacecraft came out with exactly the right speed. So the rate of use of the fuel really dropped off. Otherwise, I think we would have ended the mission much earlier.
But it's interesting, everybody that, you got an E-light now to tell you when your gas tank's empty, but everybody knows every different car, do you have 100 miles after the E-light goes? Do you have 10 miles after the E-light goes? So we're measuring a 2,000 kilogram tank, and we were down at 10 plus or minus 20 kilograms left. So the E-light had been on for 40 years.
Last but not least, PSW member Gary Liss.
Gary Liss, Johns Hopkins University Applied Physics Lab, and astronomer colleague of many of the people up on the stage. So I have 3 questions, hopefully quick. One is there a chronoseismological mode that could possibly excite the polar hexagon you see on the north pole of Saturn? Second question, are the red lines you see on the moon that Paul Schenck found anything like, because they're organic rich, anything like the lineaments we see on Europa, the upwelling sites? And third, it seems that on Titan it would be hard to expect impacts to bring in much water. Well, on the other hand, cryovolcanic areas could have lots of water over billions of years. So is that the place to look for life on Titan? Those are my questions.
So the answer to the first one is maybe. We think most of the waves in the sea ring are due to actual oscillations going on in the interior of the planet. We think those are deep down somewhere in the convective layers. We'd really love to know exactly what level they are in the planet. We don't know yet. But there's a slightly different set of waves that are nearby, which seem to rotate at a rate very close to the rate that the planet itself rotates. And some of them rotate at almost exactly the same rate that the hexagon itself. I showed that velocity profile of the hexagon. So we know the rotation period of that jet stream or whatever it is, and it matches some of the waves in the sea ring. So it's an intriguing possibility that maybe that hexagon extends deep down enough into Saturn to perturb the gravity field enough to affect the ring. So it's possible, yeah.
Would they be symmetric modes? Do you also expect the hexagon at the South Pole?
There is no hexagon at the south, which is peculiar.
Right.
Yeah.
Okay, the second question about the red streaks on Tethys. They're totally unlike the ridges on either Enceladus or Europa because they're painted onto the surface. The ridges or the tiger stripes or the cycloidal features or the triple bands or whatever, the lineaments on Europa, whatever you want to call them, they're structural, they're geologic features. These are just, painted features. Now, they do seem to follow some vague concentric ring, which might imply some tidal force possibly led to their formation, but it's imperfect. Their position is imperfect. They seem to be compositionally distinct from the surrounding areas, but particle size may also be an effect. We haven't been able to really straighten that out yet.
So I think your final question was about Titan. It was a question about could impacts bring in liquid water to
Microphone.
That impacts probably couldn't bring in enough water over billions of years to support life. On the other hand, upwelling cryovolcanic in an area that's continuously experiencing cryovolcanism could. So is that the place to look for life on Titan?
So that's a great question. That's one of the things we're going to study in our astrobiology project. One of the questions that we set out to try and answer on Titan, this is a mystery that I didn't really go into, is why Titan has an atmosphere at all. And in fact, it really is the only moon that has a substantial atmosphere. We don't know why. It could be that it's being continuously replenished from the interior. That's one of the theories. So one of the things we did in the Cassini mission looking for was activity, geological activity on Titan, and we never found anything conclusive. Part of the problem is it's just so hard to look through Titan's atmosphere. So there were some radar maps on the surface that showed some things that looked like they could be volcanic cones, but it was very, very tenuous. So that's a question we still don't know the answer. Is Titan geologically active? So we can think, for liquid water, we can think of either what we call endogenous, which is the cryovolcanism, or the exogenous, which is the meteorite impacts. And you're right, there's probably not enough meteor strikes to keep the surface liquid, but maybe transient events. I think the best possibility is probably deep inside Titan. But the search for the cryovolcanism is something that's going to go on. And actually, the Dragonfly mission is one of the missions that actually maybe could get us closer to the answer to that.
Correct me if I'm wrong. Aren't there 2 or 3 spots that are thought to be cryovolcanoes or have been identified as such? Am I mistaken? So
we just wrote a review paper on this, and I'll point you to it, but it's still controversial. It actually excites some very heated debate. So there have been some people on the team who have come out and said, yes, there is. We see these kind of low-bait flow fronts, definitely cryovolcanism, and others have come back and said, no, it's just a trick of the light, or you look at it in a different way, it doesn't look the same thing. And I would say there's nothing conclusive right now. The best evidence we have, there's a structure which is looks kind of like a volcano. It's actually called Mount Doom. So you can see there's some Tolkien fans on the team, but it's such a kind of low-resolution map right now that it's all blocky, and it's really, really hard to tell if it's really a volcano or not. But that's a place that maybe to go back for another look. Yeah.
I think I'm going to ask the speakers to sit tight for a minute, and I'm going to do a few closing remarks and adjourn to the social hour very quickly. So first of all, an appreciation for the speakers coming here, some from afar, and for giving these wonderful talks and giving us a little insight into a lot more that we know about Saturn because of Cassini. I have for each of them a framed copy of the announcement of the lecture and a signed copy of the Volume 1 of the Philosophical Society of Washington, which has a little special interest because it describes why the society was formed, who the founders were, and explains a little bit why they picked philosophical for their title, which they meant science, really, but okay. So if you'll give our speakers a nice warm round of applause. I'm going to show the movie. At the end. So I'm going to put a movie up at the end, which is the Cassini finale animation that JPL produced. But before then, just a few housekeeping announcements. Before we adjourn to the social hour, first of all, we need members. PSW is a charitable nonprofit organization. It's a membership organization, and part of our nonprofit status depends on having a certain amount of our revenue come from members. So I would urge you, if you're not a member, please join. Joining is really easy. You just go to the website, which will shortly look very different than this, and you click on the membership button, and you get the application for membership, which you can fill out forthwith. Get to a submit the form, brings up a dues payment form. You pay dues if we decide not to accept your membership, which is highly unlikely. We will refund your dues. I urge you to do that. I hope you will. And just keep in mind, PSW is tax exempt under Section 501c3 of the Internal Revenue Code for now. Contributions are tax deductible. Okay. These lectures end the spring lecture series, and we are working on the fall lecture series, and we will post the schedule of the fall lectures in the coming weeks or maybe early August. Please keep an eye on the PSW website for updates, www.pswscience.org. And the social hour will end about 11, given the late hour of adjournment. And thereafter, PSW members and guests go across the street to the Fairfax Hotel. I believe we're in the lobby now because the lounge is being renovated. If you're interested in joining us, please see corresponding Secretary Robin Taylor and the guy in the bright green shirt in the back of the room, our membership director, Lloyd Taylor. With that, I will accept a motion for adjournment with one note. I am going to run this film shortly. Or maybe I could run it before adjournment. It's only 30 seconds.
This one's only a minute.
Everybody will be able to see.
Sandworks.
On the final orbit, Cassini would plunge into Saturn, keep its antenna pointing at Earth as it transmits its pheromone. In the skies of Saturn, the journey ends as Cassini becomes part of the planet itself.
Accept a motion for adjournment. The meeting is adjourned to the social hour.